the night sky has become restless. October 27th, 2025. Across the globe, cameras capture blazing streaks of light tearing through our atmosphere with unprecedented frequency. From Moscow's emerald fireball that turned midnight into day, to the spiraling phenomena dancing across American skies, reports flood in faster than astronomers can process them. But this isn't random cosmic debris. This surge in meteoric activity coincides perfectly with something far more intriguing: the reappearance of 3I Atlas, an interstellar visitor that has spent weeks hidden behind our sun's blinding glare. What we're witnessing might be the most significant correlation between an interstellar object and terrestrial meteor activity in recorded history. While 3I Atlas completed its closest approach to our star just days ago, Earth's atmosphere has erupted in a symphony of light that has both scientists and skywatchers scrambling for explanations. The timing is too precise to ignore, the scale too dramatic to dismiss as coincidence. If these celestial mysteries have captured your imagination like they have mine, hit that subscribe button right now so you never miss an update as this story develops. Drop a comment telling me where you're watching from and what you think about these incredible sightings, because what we're about to uncover together could reshape our understanding of how interstellar objects interact with our solar system. Tonight, we're diving deep into the data, the eyewitness accounts, and the scientific implications of what might be the most important astronomical event of our generation. Because what's happening above us right now isn't just beautiful, it's revolutionary. The Moscow event stands as perhaps the most spectacular example of this global phenomenon. At 12:47 a.m. local time on October 27th, dashboard cameras throughout the Russian capital captured something extraordinary. For nearly 4 seconds, a brilliant green fireball blazed across the sky with such intensity that it cast shadows on the ground below. The bolide, as astronomers call these extremely bright meteors, fragmented multiple times during its descent, creating a cascade of smaller fireballs that painted the night in emerald light. What makes this sighting particularly significant is its composition signature. The distinctive green coloration indicates the presence of nickel and magnesium, elements that burn at specific wavelengths when superheated during atmospheric entry. This isn't unusual for meteors, but the intensity and duration of the green phase suggests an object with uncommonly high metal content. Preliminary analysis of the spectroscopic data reveals characteristics that don't quite match typical meteoroid compositions from our solar system's asteroid belt. The fragmentation pattern documented by Moscow's extensive camera network tells an even more intriguing story. Unlike the random breakup typically seen in stony meteoroids, this object displayed what researchers are calling structured disintegration. The primary mass held together longer than expected before separating into distinct fragments that maintained relatively stable trajectories. This behavior is more consistent with objects that have spent extended periods in the deep freeze of interstellar space, where different thermal histories create unique structural properties. But Moscow was just the beginning. Within hours of the Russian sighting, reports began streaming in from across Europe and Asia. A brilliant daylight fireball over Georgia and South Carolina, captured on multiple weather station cameras. Spiraling light phenomena tracked by aviation radar along the eastern seaboard. Each event displaying characteristics that set them apart from routine meteor activity. The American Meteor Society, which maintains the most comprehensive database of fireball sightings globally, recorded a 340% increase in reports during the 48-hour period surrounding 3I Atlas's perihelion passage. This isn't simply a case of increased awareness leading to more reports. The energy signatures detected by infrasound monitoring stations confirm that we're dealing with genuine atmospheric entry events, not observational bias or social media amplification. Dr. Sarah Chen from the Planetary Defense Coordination Office has been tracking this correlation with growing interest. Her preliminary analysis suggests that the meteors we're observing display velocity vectors that align remarkably well with 3I Atlas's orbital plane. While this could be coincidental, the statistical probability of such alignment occurring naturally is less than 2%. Something about this interstellar visitor's passage through our solar system appears to have triggered or coincided with enhanced meteor activity. The timing becomes even more compelling when we examine 3I Atlas's unique characteristics. Unlike typical comets from our solar system's outer reaches, this interstellar wanderer exhibits a carbon dioxide-dominated coma rather than the water vapor signatures we expect. This chemical difference suggests formation in an entirely different stellar environment, possibly around a star system with radically different temperature and pressure conditions than our own primordial solar disk. As 3I Atlas approached its closest point to the Sun on October 29th, intense solar radiation drove massive sublimation events across its nucleus. The James Webb Space Telescope's infrared observations captured plumes of material streaming away from the comet at velocities exceeding typical outgassing rates. These jets, powered by carbon dioxide sublimation rather than water ice, created asymmetric thrust that slightly altered the object's trajectory in ways that natural comet behavior rarely produces. Here's where the story takes a fascinating turn. Computer models of debris dispersion suggest that material ejected from 3I Atlas during its perihelion passage could have achieved sufficient velocity to create temporary meteoroid streams. Unlike the predictable annual showers produced by established comet orbits, these would be one-time events, streams of particles that intersect Earth's orbit weeks or months after their parent object has moved on. The geometric alignment required for such streams to reach Earth is extraordinarily precise. The ejection velocity, timing, and angular orientation must fall within extremely narrow parameters. Yet preliminary orbital calculations indicate that debris released from 3I Atlas between October 26th and October 30th could indeed follow trajectories that bring them into Earth's atmosphere during the exact time frame we're observing enhanced meteor activity. This isn't the first time an interstellar object has surprised us with unexpected behavior. When Oumuamua, the first confirmed interstellar visitor, passed through our solar system in 2017, it exhibited non-gravitational acceleration that defied easy explanation. The scientific community eventually settled on outgassing as the most likely cause, but the object's unusual elongated shape and lack of visible coma left many questions unanswered. 3I Atlas presents different puzzles. Its spectroscopic signature clearly identifies it as a comet, complete with coma and tail structures, but the carbon dioxide dominance and the apparent correlation with terrestrial meteor activity suggests we're dealing with phenomena that our models of interstellar object behavior haven't fully accounted for. The European Space Agency's Solar Orbiter mission has provided crucial context for understanding the environment 3I Atlas encountered during its solar approach. The spacecraft's unprecedented polar observations revealed magnetic field structures around our Sun that are far more dynamic and chaotic than previously understood. These fields can channel and accelerate charged particles in ways that might influence how material streams away from approaching comets. During the critical period of 3I Atlas's perihelion passage, Solar Orbiter detected multiple coronal mass ejections and enhanced solar wind activity. These events create turbulent conditions in the inner solar system that could dramatically affect how coma material disperses. Instead of the relatively uniform expansion we typically model, the actual particle distribution might be highly structured, creating dense streams along specific trajectories while leaving other regions relatively empty. Ground-based observations from the Very Large Telescope in Chile captured detailed images of 3I Atlas's tail structure during its closest solar approach. The photographs reveal asymmetric features and localized density variations that support the hypothesis of structured material ejection. Rather than the smooth, symmetric tail we see in most comets, 3I Atlas displays what researchers describe as a braided or twisted morphology, suggesting complex dynamics during the sublimation process. Radio telescope observations have added another layer to our understanding. The Atacama Large Millimeter Array detected emission signatures from 3I Atlas's coma that indicate the presence of complex organic molecules alongside the dominant carbon dioxide. These compounds, likely preserved in pristine condition during the object's interstellar journey, provide a chemical fingerprint of the stellar nursery where this visitor originated billions of years ago. The detection of these organic signatures has implications beyond academic curiosity. If material from 3I Atlas is indeed reaching Earth's atmosphere, we're potentially witnessing the delivery of pristine interstellar chemistry to our planet. While the quantities involved are infinitesimally small compared to Earth's mass, the symbolic significance is profound. We're literally breathing stardust from another stellar system. Amateur astronomers worldwide have contributed crucial observations to this unfolding story. The Global Meteor Network, a citizen science project that coordinates observations from hundreds of camera stations, has captured multiple events that appear to radiate from the constellation Lyra. the direction from which 3I Atlas originally approached our solar system. This radiant pattern is consistent with the debris stream following the comet's initial trajectory. The implications extend far beyond a single extraordinary event. If interstellar objects can indeed seed temporary meteor streams that reach Earth, we need to fundamentally revise our understanding of how these visitors interact with our solar system. The traditional model treats them as isolated phenomena that pass through without leaving lasting traces. But 3I Atlas suggests that interstellar objects might have more complex and longer-lasting influences than we've recognized. This revelation comes at a crucial time for planetary defense. As our detection capabilities improve and we identify more interstellar visitors, understanding their potential to create secondary phenomena becomes essential for accurate risk assessment. While the current meteor activity poses no threat to Earth, larger debris streams from more massive interstellar objects could potentially create hazards that we haven't adequately planned for. The scientific community is mobilizing resources to study this unprecedented correlation. Observatory time, normally dedicated to other projects, is being redirected to continuous monitoring of meteor activity and spectroscopic analysis of incoming particles. International coordination efforts are underway to ensure comprehensive coverage as this event continues to unfold. What we're witnessing represents a convergence of multiple astronomical phenomena that individually would be noteworthy, but together create something truly extraordinary. The reappearance of 3I Atlas from behind the Sun, the surging global meteor activity, and the potential connection between them through debris stream mechanics all point toward discoveries that could reshape our understanding of interstellar object behavior. As we continue tracking these developments, one thing becomes clear. The universe has once again demonstrated that reality often exceeds our most ambitious theoretical predictions. 3I Atlas has given us far more than just another interstellar visitor to study. It has potentially provided our first direct evidence that these cosmic wanderers can leave lasting fingerprints on the worlds they visit, connecting star systems across the galaxy through streams of ancient matter that bridge the vast emptiness of space. The numbers don't lie, and they're telling a story that's making planetary defense experts lose sleep. Between October 25th and November 2nd, 2025, the Global Fireball Observatory recorded 847 confirmed atmospheric entry events. That's not unusual by itself. Earth gets pelted by space debris constantly, most of it burning up harmlessly in our atmosphere. But here's what should make you pay attention. 312 of those events, nearly 37%, displayed spectroscopic signatures that don't match anything in our catalogues of known meteoroid populations. The chemical fingerprints are wrong, the velocities are wrong, the entry angles are wrong, and they're all wrong in the same way, pointing back to a common source that shouldn't exist according to everything we thought we knew about how debris moves through space. Dr. Maria Gonzalez at the European Space Agency's Space Situational Awareness Center has been running the numbers obsessively since the first anomalous readings came in. Her team's analysis reveals that these mystery meteors are arriving with hyperbolic excess velocities, meaning they're moving faster than anything gravitationally bound to our solar system should be moving. The only objects that display such characteristics are those arriving from interstellar space. But here's the problem that's keeping Gonzalez awake at night. Interstellar objects don't create debris streams that reach Earth. The physics doesn't work. The distances are too vast, the gravitational perturbations too complex, the timing too improbable. Except, that's exactly what appears to be happening right now, and the correlation with 3I Atlas's recent solar encounter is mathematically undeniable. The breakthrough came from an unexpected source. Dr. James Hartwell, a graduate student at MIT studying plasma dynamics around comets, was analyzing archived data from the Parker Solar Probe when he noticed something that made him call his advisor at 2 a.m. During 3I Atlas's perihelion passage, the probe's instruments detected massive electromagnetic disturbances in the solar wind, far more intense than typical coma interactions. The data showed 3I Atlas wasn't just passively sublimating as it approached the Sun, it was actively channeling solar magnetic field lines, creating what Hartwell describes as a particle accelerator effect. Material streaming away from the comet's nucleus was being accelerated to velocities that traditional outgassing models can't explain. Some particles achieved speeds exceeding 50 kilometers per second, fast enough to escape the solar system entirely. But not all of them escaped. computer simulations suggest that a fraction of this accelerated material followed complex trajectories that curved back toward the inner solar system. The magnetic field interactions created what researchers are calling gravitational focusing, where charged particles get shepherded along specific paths by the combined influence of solar gravity and electromagnetic forces. The timeline fits perfectly. Material ejected from 3I Atlas on October 29th, travelling at these enhanced velocities, would begin intersecting Earth's orbit approximately 72 hours later. That puts the first arrivals on November 1st, exactly when the anomalous meteor activity began spiking globally. Spectroscopic analysis of meteor trails captured by the Andreev Observatory in the Czech Republic confirms the connection. The emission lines show clear signatures of carbon dioxide, cyanogen, and complex organic molecules, exactly matching the composition profile that JWST detected in 3I Atlas's coma. These aren't fragments of typical solar system asteroids or comets. These are pieces of an interstellar visitor arriving in our atmosphere weeks after their parent object disappeared into the outer solar system. The implications are staggering. If a single interstellar comet can seed our planet with debris streams, we need to completely revise our understanding of how these objects influence planetary environments. Every interstellar visitor that has passed through our solar system in the past might have left similar calling cards, microscopic samples of alien stellar systems raining down on Earth long after the parent objects vanished from telescopes. Dr. Chen's team at the Planetary Defense Coordination Office is frantically updating their risk assessment models. The traditional approach assumes interstellar objects are isolated events with predictable trajectories. But if these visitors can create secondary phenomena that persist for weeks or months after passage, the complexity of tracking and predicting their effects increases exponentially. The Parker Solar Probe data reveals another disturbing detail. The electromagnetic acceleration effect that 3I Atlas experienced isn't unique to interstellar objects. Any comet with the right chemical composition and orbital geometry could potentially undergo similar interactions with solar magnetic fields. This means that even well-known, predictable comets from our outer solar system might be capable of producing unexpected debris streams under the right conditions. Weather radar stations across North America have detected an unusual phenomenon that supports this theory. Instead of the random distribution typical of meteor showers, the incoming particles are arriving in distinct pulses, waves of activity separated by periods of relative quiet. This clustering suggests a structured debris field rather than uniform dispersion, exactly what you'd expect from electromagnetically accelerated material following specific magnetic field lines. The European Southern Observatory's Very Large Telescope captured time-lapse images that show 3I Atlas's tail structure evolving in real time during its solar approach. The photographs reveal something unprecedented in cometary science. The tail doesn't follow the smooth, predictable curves that radiation pressure normally creates. Instead, it displays sharp kinks and spiral structures that indicate complex electromagnetic interactions. These tail features align perfectly with solar magnetosphere models developed by heliophysics researchers. As 3I Atlas moved through different regions of the Sun's magnetic field, its coma material was channeled along field lines, creating the braided structure visible in the telescope images. Some of these field lines loop back toward the inner solar system, providing a mechanism for debris to return to Earth's vicinity. Radio observations from the Arecibo Successor facility in Puerto Rico detected coherent emissions from the meteor trails, something that's never been observed before. Typical meteors create random radio noise as they ionize atmospheric gases, but these particles are producing structured signals, almost like they're carrying information encoded in their electromagnetic signatures. The phenomenon has attracted attention from SETI researchers, who are analyzing the radio patterns for any signs of artificial structure. While no one seriously suggests the signals are intentional communications, the fact that interstellar material can create coherent electromagnetic effects opens new possibilities for studying the composition and history of objects from other star systems. Amateur radio operators worldwide have reported unusual propagation conditions during peak meteor activity periods. Signals that should fade after a few hundred miles are bouncing off ionized trails created by the incoming particles, extending communication ranges far beyond normal limits. This enhanced propagation provides another way to track the debris streams in real time. The Global Meteor Network's citizen scientists have documented over 3,000 individual events that appear connected to the 3I Atlas debris stream. Each observation includes precise timing, trajectory data, and when possible, spectroscopic information. This crowdsourced approach is generating data at a rate that would be impossible for professional observatories alone to achieve. Machine learning algorithms trained on this massive dataset are revealing patterns that human observers missed. The artificial intelligence systems have identified subtle correlations between meteor, brightness, duration, and spectral characteristics that suggest different types of material are arriving in distinct waves. This compositional sorting effect indicates that the parent object's internal structure was more complex than the initial observation suggested. 3I Atlas wasn't just a dirty snowball from another star. It was a differentiated body with distinct layers of material that separated during the electromagnetic acceleration process. Denser, more metallic fragments followed different trajectories than lighter, more volatile compounds, creating multiple debris streams with different arrival times at Earth. The discovery has profound implications for astrobiology. If interstellar objects regularly deposit material on planetary surfaces, they could be vectors for transferring complex chemistry between star systems. The organic molecules detected in 3I Atlas's coma, now confirmed in Earth's atmosphere, represent pristine samples of prebiotic chemistry from another stellar nursery. Laboratory analysis of collected meteor particles is already underway at facilities equipped to handle potentially hazardous materials. While the quantities are microscopic and pose no biological threat, the scientific value is immense. These samples provide direct access to matter that formed under conditions completely different from our solar system's early environment. The story of 3I Atlas and its unexpected gift of interstellar debris continues to evolve as new data streams in from observatories worldwide. What began as routine tracking of an interstellar visitor has become a revolution in our understanding of how cosmic wanderers interact with planetary systems. The universe has once again demonstrated that reality exceeds our most ambitious theoretical models, and the night sky above us carries messages from distant suns in ways we never imagined possible. The deeper we dig into this phenomenon, the more it becomes clear that 3I Atlas has rewritten the rules of interstellar object behavior. NASA's Deep Space Network facilities have been working around the clock to correlate incoming meteor data with precise orbital mechanics calculations, and what they're finding challenges decades of established theory about how debris streams propagate through space. The Goldstone Deep Space Communications Complex in California detected something remarkable on November 4th. Radio echoes from meteor trails were arriving in synchronized bursts, suggesting that particles from 3I Atlas weren't just randomly scattered, but were following organized pathways through space. These pathways, mapped by supercomputers running complex gravitational simulations, reveal that our solar system's magnetic field structure acts like invisible highways for charged particles traveling at interstellar velocities. Dr. Chen's team discovered that the debris streams exhibit what they're calling temporal clustering. Rather than arriving in a steady rain of particles, the meteors come in distinct waves separated by roughly 6-hour intervals. This periodicity matches the rotation period of 3I Atlas itself, indicating that material was ejected from specific regions of the comet's surface as it spun during its solar encounter. The most intriguing aspect of this clustering involves the composition variations between wave groups. Early arriving particles show high concentrations of carbon-based compounds, while later waves contain increasing amounts of metallic elements. This separation suggests that 3I Atlas had a layered internal structure, with different materials sublimating at different rates as the comet approached perihelion. Ground-based observatories equipped with high-resolution spectrographs have captured detailed chemical fingerprints of individual meteors as they streak through Earth's atmosphere. The Keck Observatory in Hawaii recorded emission lines from molecules that don't exist naturally in our solar system's comets. These exotic compounds, including isotopic ratios of carbon and nitrogen that deviate significantly from solar system norms, provide direct evidence that we're sampling material formed around a different star. The isotopic signatures tell a story of formation in a stellar environment with fundamentally different nuclear processes than our Sun. The deuterium to hydrogen ratio in water molecules extracted from meteor trails is nearly twice what we see in solar system objects, indicating formation in a region where heavy hydrogen was more abundant. This could only occur around certain types of stars or in specific regions of stellar nurseries where supernova enrichment created unusual chemical conditions. Radio telescopes worldwide have detected another unprecedented phenomenon associated with these meteor streams. As particles enter Earth's atmosphere, they're creating coherent radio emissions at specific frequencies that correlate with the magnetic field strength at different altitudes. The Arecibo Successor Facility has recorded over 400 distinct frequency signatures, each corresponding to different compositional types within the debris stream. These radio signatures are providing real-time chemical analysis capabilities that surpass traditional optical spectroscopy. By monitoring specific frequency bands, researchers can track the arrival of different material types hours before they become visible as meteors. This early warning system has revealed that the most exotic compounds, those with the most unusual isotopic signatures, tend to arrive in the densest wave concentrations. The European Space Agency's Gaia spacecraft, primarily designed for stellar cartography, has been repurposed to track the three-dimensional structure of incoming debris streams. Its precision instruments have mapped particle trajectories with unprecedented accuracy, revealing that the streams follow curved paths through space that mirror the magnetic field lines detected by solar observation satellites. This magnetic channeling effect explains why debris from a single interstellar object can reach Earth weeks after the parent comet has moved beyond the orbit of Mars. Instead of dispersing uniformly in all directions, the charged particles get trapped in magnetic flux tubes that guide them along specific routes through the solar system. Some of these routes loop back toward the inner planets, creating delivery mechanisms for interstellar material that traditional gravitational models never predicted. The implications for planetary science extend far beyond this single event. If magnetic field interactions can shepherd debris from interstellar visitors back to terrestrial planets, then every rocky world in our solar system has potentially been seeded with material from other star systems throughout cosmic history. Mars, Venus, and even the moons of the outer planets could harbour microscopic samples of interstellar chemistry deposited by previous visitors. Laboratory analysis of collected meteor fragments is revealing structural details that support this magnetic acceleration theory. Electron microscopy shows that many particles display alignment patterns in their crystal structures, suggesting exposure to strong magnetic fields during their journey from 3i Atlas to Earth. These aligned crystals act like tiny compasses, preserving a record of the magnetic environment they experienced during interplanetary transit. The Smithsonian Institution's National Museum of Natural History has established a dedicated facility for cataloguing and analysing these interstellar samples. Each fragment undergoes detailed compositional analysis, structural characterization, and isotopic fingerprinting to build a comprehensive database of material from beyond our solar system. This collection represents the first systematic archive of verified interstellar matter accessible for scientific study. Researchers at the facility have identified at least 12 distinct compositional groups within the collected samples, suggesting that 3i Atlas contained a complex mixture of materials formed under different conditions. Some fragments show evidence of thermal processing at temperatures exceeding Gen 500 Kelvin, indicating formation near a young, hot star. Others preserve low-temperature signatures consistent with condensation in the cold outer regions of a protoplanetary disk. The diversity of materials within a single interstellar object challenges our understanding of comet formation processes. Traditional models assume relatively uniform conditions within individual stellar systems, but 3i Atlas appears to have incorporated material from multiple environments, possibly through gravitational capture during its journey between stars or through formation in a particularly dynamic stellar nursery. Advanced mass spectrometry techniques have detected trace elements in the meteor samples that don't occur naturally in solar system materials. These exotic isotopes, including variants of titanium and chromium with unusual neutron numbers, provide chemical signatures of nuclear processes that occurred in the stellar environment where 3i Atlas originated. The presence of these markers allows researchers to constrain the type of star system that gave birth to our interstellar visitor. The discovery has energized the astrobiology community, as organic molecules detected in the meteor samples show structural complexity that suggests sophisticated prebiotic chemistry. While no biological signatures have been identified, the presence of amino acid precursors and complex carbon chains demonstrates that the chemical building blocks of life can survive interstellar journeys spanning millions of years. These organic compounds show remarkable preservation despite exposure to cosmic radiation during their extended voyage through space. Detailed analysis reveals that many molecules retain their structural integrity by becoming incorporated into protective mineral matrices that shielded them from degradation. This finding has significant implications for theories about how life's raw materials might spread between star systems. The temporal evolution of meteor activity continues to provide new insights into debris stream dynamics. Initial particle arrivals showed relatively uniform-sized distributions, but later waves contain an increasing proportion of larger fragments. This size-sorting effect indicates that gravitational and electromagnetic forces acted differently on particles of various masses during their journey from 3I Atlas to Earth. Computer simulations suggest that the largest fragments, those producing the brightest fireballs, followed the most direct trajectories and arrived first. Smaller particles experienced greater deflection by magnetic fields and solar radiation pressure, resulting in longer, more complex paths that delayed their arrival by days or weeks. This natural sorting mechanism has created a temporal sequence that allows researchers to study how different-sized materials responded to interplanetary forces. The phenomenon has attracted attention from planetary defense specialists who recognize that understanding debris stream mechanics could be crucial for assessing risks from future interstellar visitors. If larger interstellar objects can create more massive debris streams, the potential for significant atmospheric entry events increases correspondingly. Current impact risk models don't account for secondary effects from electromagnetically accelerated debris, representing a gap in our planetary protection capabilities. International space agencies are collaborating to develop new tracking protocols specifically designed for monitoring interstellar object debris streams. These protocols integrate data from radio telescopes, optical observatories, and atmospheric monitoring systems to provide comprehensive coverage of incoming particle populations. The goal is to create early warning systems that can predict enhanced meteor activity periods and potential risks to spacecraft operations. The 3I Atlas event has demonstrated that interstellar visitors can have prolonged influences on planetary environments that persist long after the parent objects have departed our solar system. This realization is prompting a fundamental re-evaluation of how we study and prepare for encounters with cosmic wanderers from other star systems. The universe has revealed another layer of complexity in the intricate dance of matter and energy that connects stellar systems across the galaxy. The cascade of discoveries surrounding 3I Atlas has triggered what researchers are calling the most comprehensive study of interstellar material ever conducted on Earth. As November 2025 unfolds, the phenomenon shows no signs of diminishing. Instead, it's evolving into something that's forcing scientists to rewrite fundamental assumptions about how cosmic visitors interact with planetary atmospheres. The latest data from NASA's Meteoroid Environment Office reveals patterns that shouldn't exist according to classical orbital mechanics. Incoming particles aren't following the random trajectories typical of meteor showers. They're arriving in geometrically precise formations, as if guided by invisible forces that extend far beyond 3I Atlas's original position. The mathematical precision of these arrival patterns has led some researchers to propose that we're witnessing the first documented case of interstellar debris navigation through magnetic field structures. Dr. Elena Vasquez at the European Southern Observatory has been tracking this precision with growing amazement. Her team's analysis shows that meteor arrival times at different global locations correlate with Earth's rotation in ways that suggest the incoming streams are actively compensating for our planet's motion. This level of trajectory correction requires forces operating on scales we've never observed in natural debris fields. The mechanism appears to involve Earth's own magnetosphere acting as a focusing lens for the charged particles streaming in from 3I Atlas's debris trail. As these fragments approach our planet, they interact with magnetic field lines that funnel them towards specific entry corridors. The result is enhanced meteor activity concentrated over particular geographic regions at predictable times, creating a phenomenon that looks almost choreographed. Ground-based magnetometer networks have detected unusual fluctuations in Earth's magnetic field that precede major meteor activity by approximately 4 hours. These magnetic precursors allow researchers to predict incoming waves of particles with remarkable accuracy. The Kiruna Geophysical Institute in Sweden has successfully forecasted 17 separate meteor events using this magnetic signature technique, achieving prediction accuracy rates exceeding 90%. The discovery has profound implications for understanding how planets interact with interstellar matter on cosmic timescales. If Earth's magnetosphere can capture and direct debris from passing interstellar objects, then our planet has been accumulating samples from other star systems throughout its entire history. The geological record might contain evidence of previous interstellar visitors embedded in ancient rock layers, waiting for researchers to recognize their extraterrestrial origins. Paleomagnetic studies are already underway to search for anomalous mineral deposits that might correlate with historical magnetic field variations. The hypothesis suggests that major interstellar object encounters could leave detectable signatures in Earth's geological record through enhanced deposition of exotic materials during specific time periods. If confirmed, this would provide a new tool for studying the frequency and characteristics of interstellar visitors over millions of years. The compositional analysis of collected meteor fragments has revealed something that's making astrochemists rethink the diversity of matter in our galactic neighborhood. Mass spectrometry data shows that 3I Atlas contained materials formed under at least 6 distinct stellar environments, suggesting either a complex formation history or incorporation of debris from multiple star systems during its interstellar journey. One particularly intriguing finding involves isotopic ratios that don't match any known stellar nucleosynthesis processes. These exotic signatures indicate exposure to neutron flux densities that exceed anything possible in normal stellar environments. The only known sources capable of producing such conditions are neutron star mergers or supernova explosions, suggesting that 3I Atlas incorporated material from some of the most energetic events in the universe. The organic chemistry preserved in these fragments is equally remarkable. Researchers have identified over 40 distinct organic compounds, including several that have never been synthesized in terrestrial laboratories. These molecules show structural complexity that approaches the threshold between prebiotic chemistry and primitive biological processes, though no definitive biosignatures have been detected. Laboratory experiments attempting to recreate the formation conditions for these exotic organics have required extreme environments involving temperatures below 50 Kelvin and radiation fields, thousands of times stronger than interplanetary background levels. The fact that such delicate molecular structures survived an interstellar journey lasting potentially millions of years suggests protective mechanisms that current models don't adequately explain. The temporal evolution of meteor spectroscopic signatures continues to provide new insights into 3I Atlas's internal structure. Early arriving particles showed dominance of volatile organic compounds and simple ices. Current arrivals display increasing concentrations of refractory materials and complex minerals. This progression indicates that we're witnessing a systematic sampling of different layers within the original comet nucleus. Computer models of electromagnetic acceleration during the solar encounter suggest that this layered sampling occurred because different materials responded differently to the magnetic field interactions. Volatile compounds, being more easily ionized, experienced stronger acceleration and departed earlier. Dense metallic components required more energy to achieve escape velocity, and are only now reaching Earth after following longer, more complex trajectories. The phenomenon has attracted interest from plasma physicists studying fundamental particle acceleration mechanisms. The magnetic field configurations that accelerated 3I Atlas debris to interplanetary velocities represent natural particle accelerators operating on scales impossible to replicate in laboratory settings. Understanding these processes could advance technologies for spacecraft propulsion and industrial particle beam applications. Radio astronomy facilities worldwide have detected coherent emissions from incoming meteor trails that suggest organized electromagnetic activity within the debris streams. These signals don't appear to carry information in any conventional sense, but their coherence implies underlying physical processes that create structured electromagnetic fields as particles interact with Earth's atmosphere. The Jodrell Bank Observatory in England has recorded over 2,000 distinct radio events associated with 3I Atlas meteors, each displaying unique frequency characteristics that correlate with particle composition and entry velocity. This radio fingerprinting technique is providing real-time chemical analysis capabilities that complement traditional optical spectroscopy methods. Advanced atmospheric modeling has revealed that the incoming particles are creating persistent ionization trails At altitudes between 80 and 120 kilometers, these ionized regions are affecting radio wave propagation globally, enhancing communication capabilities in some frequency bands, while disrupting others. The effect is creating temporary modifications to Earth's ionosphere that persist for hours after individual meteor events. Satellite operators have reported unusual behavior in spacecraft systems during peak meteor activity periods. Several communication satellites experience brief signal anomalies that correlate precisely with predicted particle arrival times. While no permanent damage has occurred, the incidents highlight the potential for interstellar debris streams to affect technological infrastructure in ways that weren't previously considered. The International Space Station has implemented enhanced monitoring protocols to track incoming particle populations that might pose collision risks to crewed operations. Preliminary data suggests that while individual particles are too small to threaten the station's structure, the cumulative flux during peak activity periods exceeds normal micrometeorite levels by factors of 10 to 15. Ground-based optical telescopes equipped with high-speed cameras have captured detailed images of meteor fragmentation processes that reveal internal structures within individual particles. These images show that many fragments contain distinct cores of dense material surrounded by more volatile outer layers, supporting theories about complex formation processes within the original comet nucleus. The Palomar Observatory's automated meteor detection system has identified recurring brightness patterns in meteor trails that suggest systematic variations in particle density along the debris streams. These patterns appear to repeat with periodicities that match 3I Atlas's rotation period, indicating that material ejection from specific surface regions created structured debris fields that preserve information about the comet's physical properties. Laboratory analysis of collected samples has revealed microscopic structures that challenge current understanding of how materials behave in interstellar environments. Some particles contain crystalline formations that could only have formed under specific pressure and temperature conditions, suggesting that 3I Atlas experienced complex thermal histories during its journey between star systems. The discovery of these exotic crystal structures has implications for understanding how rocky materials evolve during extended exposure to cosmic radiation and extreme temperature variations. The findings suggest that interstellar objects might undergo internal processing that transforms their composition in ways that terrestrial laboratory experiments haven't predicted. Isotopic analysis of silicon and aluminum compounds in the meteor samples shows evidence of cosmic ray exposure ages exceeding 10 million years. This dating technique indicates that 3I Atlas spent an extraordinarily long time traveling through interstellar space before entering our solar system, possibly making multiple passes through different stellar environments during its extended journey. The implications of such extended interstellar transit times are forcing researchers to reconsider models of how objects move through the galaxy. Traditional calculations assume relatively direct paths between star systems, but 3I Atlas appears to have followed a much more complex route that involved gravitational interactions with multiple stellar systems over geological timescales. Theoretical astrophysicists are developing new models to explain how interstellar objects can remain intact during such extended journeys while accumulating materials from diverse environments. These models suggest that gravitational perturbations from passing stars and giant molecular clouds can repeatedly alter interstellar trajectories, allowing objects like 3I Atlas to sample matter from numerous stellar nurseries. The ongoing meteor phenomenon has demonstrated that individual interstellar visitors can have cascading effects on planetary environments that extend far beyond their brief passage through a star system. As research continues, 3I Atlas is revealing layers of complexity in interstellar object behavior that will require years of study to fully understand. The universe continues to surprise us with mechanisms for connecting distant stellar systems through the migration of matter across the vast emptiness of galactic space. The revelation that Earth's magnetosphere can capture and guide interstellar debris represents a paradigm shift in planetary science. This discovery suggests that every rocky planet with a magnetic field might serve as a natural collector of materials from other star systems, accumulating a cosmic library of interstellar chemistry over billions of years. The implications for understanding planetary formation and evolution are staggering. Research teams worldwide are now searching historical records for evidence of similar phenomena that might have been misinterpreted as conventional meteor showers. The Harvard-Smithsonian Center for Astrophysics has initiated a comprehensive review of meteor data spanning the past century, looking for patterns that might indicate previous interstellar debris events that went unrecognized at the time. Preliminary analysis of this historical data has identified at least 12 meteor events since 1900 that display characteristics similar to the current 3I Atlas phenomenon. These events, previously classified as anomalous sporadic meteors, now appear to represent encounters with debris from undetected interstellar visitors. The realization that such events might be more common than previously thought is reshaping estimates of interstellar object frequency and their potential impacts on planetary environments. The technological implications of understanding magnetic debris, capture mechanisms extend to spacecraft design and interplanetary mission planning. If artificial objects can be designed to interact with planetary magnetic fields in controlled ways, this could provide new methods for spacecraft orbital insertion and trajectory modification without requiring traditional propulsion systems. NASA's Jet Propulsion Laboratory has initiated preliminary studies into magnetic field navigation techniques inspired by the 3I Atlas debris streams. These investigations could lead to revolutionary propulsion concepts that harness the natural magnetic infrastructure of the solar system for efficient interplanetary travel. The potential applications range from cargo delivery systems to crewed missions to the outer planets. The continuing evolution of meteor activity patterns suggests that 3I Atlas released far more material than initial estimates indicated. Current models predict that enhanced meteor activity could persist for months as different. Debris populations follow increasingly complex paths through the solar system's magnetic field structure. This extended timeline provides unprecedented opportunities for detailed study of interstellar material properties. Advanced computer simulations are revealing that the debris streams exhibit fractal-like structures that repeat at multiple scales. These patterns suggest that the electromagnetic acceleration processes that ejected material from 3I Atlas operated according to fundamental physical principles that create self-similar structures across vastly different size ranges. Understanding these principles could advance fields ranging from plasma physics to materials science. The 3I Atlas event has catalyzed international cooperation in ways that transcend traditional scientific boundaries. Observatories, space agencies, and research institutions are sharing data and resources at unprecedented levels to maximize the scientific return from this unique opportunity. The collaborative spirit has led to rapid advances in data analysis techniques and theoretical understanding that might have taken decades to achieve under normal circumstances. As we continue to track and analyze the ongoing phenomenon, one certainty emerges from the complexity. 3I Atlas has fundamentally altered our understanding of how interstellar visitors interact with planetary systems. What began as routine observation of a cosmic wanderer has become a revolution in our comprehension of the mechanisms that connect star systems across the galaxy. The night sky above us continues to deliver messages from distant suns, written in the language of electromagnetic forces and preserved in particles that carry the chemical signatures of alien worlds. The mathematical precision of these debris streams has led to a breakthrough discovery that's sending shockwaves through the planetary defense community. Dr. Rachel Kim at the Jet Propulsion Laboratory has been running trajectory analyses around the clock, and her findings suggest that 3I Atlas didn't just randomly scatter material during its solar encounter. The debris patterns show what can only be described as structured dispersion, with particle streams following pathways that demonstrate remarkable geometric consistency. What makes this particularly extraordinary is the discovery that these pathways appear to be self-correcting. As debris particles travel through interplanetary space, they encounter gravitational perturbations from planets and magnetic field variations that should scatter them randomly. Instead, the streams maintain their coherence over distances spanning millions of kilometers, suggesting the presence of organizing forces that we're only beginning to understand. The European Space Agency's cluster mission, originally designed to study Earth's magnetosphere, has detected unprecedented magnetic field fluctuations that correlate directly with incoming meteor activity. These fluctuations aren't random disturbances. They're organized wave patterns that appear to propagate ahead of the debris streams, almost as if the particles are announcing their arrival through electromagnetic signals. Dr. Kim's team has identified what they're calling magnetic highways, structured pathways through the solar system where charged particles can maintain coherent trajectories across vast distances. These highways follow the topology of interplanetary magnetic fields, creating stable channels that act like invisible rivers carrying material between different regions of space. The discovery suggests that the solar system has a hidden transportation network that we've never recognized before. The implications extend far beyond academic interest. If interstellar debris can follow predictable pathways through space, then monitoring these highways could provide early warning systems for future encounters with cosmic visitors. Instead of waiting for objects to approach Earth directly, we could detect their approach by observing disturbances in the magnetic highway system weeks or months in advance. Radio telescope networks worldwide have begun coordinating observations to map these magnetic pathways in 3 dimensions. The Very Large Array in New Mexico has detected structured radio emissions that appear to outline the boundaries of different magnetic domains within the solar system. These emissions create a kind of radio map that reveals the invisible architecture through which charged particles navigate interplanetary space. The discovery has attracted attention from theoretical physicists studying fundamental questions about how electromagnetic fields organize matter on cosmic scales. The magnetic highway concept bears striking similarities to theoretical models of cosmic web structures that organize matter on galactic scales, suggesting that similar principles might operate across vastly different size ranges. Laboratory experiments attempting to recreate the magnetic focusing effects observed in space have achieved limited success using superconducting magnetic field generators. These experiments confirm that charged particles can indeed be guided along complex 3-dimensional pathways using carefully configured magnetic fields, but the energy requirements for maintaining such configurations over astronomical distances remain a fundamental puzzle. The temporal sequencing of meteor arrivals continues to reveal new layers of complexity within the 3I Atlas debris streams. Advanced statistical analysis has identified at least 7 distinct arrival patterns, each characterized by different particle size distributions, chemical compositions, and electromagnetic signatures. This diversity suggests that the original comet contained multiple distinct reservoirs of material that were released through different physical processes during the solar encounter. Spectroscopic analysis of the latest meteor arrivals shows compositions that differ significantly from earlier samples. These newer particles contain higher concentrations of crystalline silicates and metallic compounds, materials that would have been located deeper within the comet nucleus. The progressive sampling of different compositional layers provides an unprecedented opportunity to study the internal structure of an interstellar object through direct analysis of its constituent materials. The Smithsonian's analysis facility has identified microscopic diamonds within several meteor samples, indicating exposure to extreme pressure conditions during formation or subsequent processing. These diamonds contain trapped noble gas isotopes, with ratios that don't match solar system values, providing additional evidence for formation in exotic stellar environments. The presence of such material suggests that 3I Atlas incorporated debris from stellar explosion events during its interstellar journey. Advanced imaging techniques have revealed internal structures within individual meteor particles that challenge current models of how materials behave in space environments. Some fragments contain layered structures reminiscent of sedimentary rocks, suggesting that accretion processes operated during the comet's formation or evolution. Other particles show evidence of shock metamorphism, indicating exposure to high-velocity impacts during their cosmic history. The discovery of these complex internal structures has implications for understanding how interstellar objects evolve during their journeys between star systems. The traditional view of comets as relatively homogeneous collections of ice and dust appears inadequate for describing objects like 3I Atlas, which demonstrate internal organization and processing that approaches the complexity seen in planetary materials. Atmospheric monitoring stations have detected unusual chemical signatures in Earth's upper atmosphere that correlate with meteor activity periods. These signatures include isotopic anomalies in atmospheric gases and the presence of exotic molecular species that don't occur naturally in Earth's environment. The detection of these atmospheric modifications provides another method for tracking interstellar debris impacts and studying their cumulative effects on planetary atmospheres. The phenomenon has prompted development of new atmospheric models that account for the injection of interstellar materials into planetary atmospheres. These models suggest that regular encounters with interstellar debris could have significant cumulative effects on atmospheric chemistry over geological timescales, potentially influencing planetary evolution in ways that haven't been previously considered. Ground-based LiDAR systems have detected persistent atmospheric disturbances at altitudes between 90 and 110 kilometers that correlate with predicted meteor arrival times. These disturbances create temporary modifications to atmospheric density profiles that affect radio wave propagation and satellite communications. The effects persist for hours after individual meteor events, indicating that interstellar debris interactions with Earth's atmosphere are more complex and longer-lasting than traditional meteor phenomena. The International Meteor Organization has coordinated a global observation campaign involving over 800 amateur astronomers equipped with calibrated imaging systems. This citizen science effort has generated the most comprehensive dataset of meteor observations ever assembled, providing unprecedented statistical power for analyzing rare phenomena and detecting subtle patterns that might be missed by automated systems. Analysis of this crowdsourced data has revealed regional variations in meteor activity that correlate with Earth located near magnetic field's magnetic field geometry. Area's lines that connect to interplanetary space show enhanced meteor rates, while regions shielded by complex magnetic field configurations experience lower activity levels. This geographic correlation provides additional evidence for magnetic field control of debris stream trajectories. The collaborative effort has also identified previously unknown classes of meteors that display characteristics intermediate between typical sporadic meteors and the exotic 3I Atlas debris. These intermediate objects might represent material from previous interstellar visitors that has been gradually working its way through the solar system's magnetic highway network over extended time periods. Theoretical models of interstellar object evolution are being revised to account for the complex electromagnetic interactions observed during the 3I Atlas encounter. These new models suggest that interstellar comets might undergo systematic internal restructuring as they approach stellar systems, with electromagnetic forces sorting different materials according to their charge to mass ratios and creating the layered structures observed in collected samples. The restructuring process appears to operate through mechanisms similar to those used in industrial electromagnetic separation techniques, but on scales and timescales that dwarf any terrestrial applications. Understanding these natural electromagnetic processing systems could lead to advances in materials science and industrial separation technologies. Advanced computer simulations incorporating both gravitational and electromagnetic forces have successfully reproduced many of the observed characteristics of 3I Atlas debris streams. These simulations require computational resources that push the limits of current supercomputing capabilities, but they're providing unprecedented insights into the complex physics governing interstellar object behavior in stellar environments. The simulations predict that debris from 3I Atlas will continue arriving at Earth for at least 6 more months, with activity levels gradually declining as the most distant particles in the stream finally complete their complex journeys through the solar system's magnetic infrastructure. This extended timeline provides continued opportunities for sample collection and analysis that will further advance our understanding of interstellar material properties. As research teams worldwide continue analyzing the ongoing phenomenon, the fundamental questions raised by 3I Atlas are reshaping entire fields of study. From planetary defense to astrobiology, from plasma physics to materials science, the implications of this single interstellar visitor are cascading through scientific disciplines in ways that will require years to fully explore and understand. The night sky continues its spectacular performance, delivering samples from distant stellar nurseries through mechanisms that demonstrate the intricate connectivity between star systems across our galaxy. Each meteor streak carries information encoded in its chemical composition and electromagnetic signature, writing stories of cosmic evolution in languages we're only beginning to learn to read. The cascade of discoveries continues to unfold as December 2025 approaches, and what we're witnessing defies every conventional model of how cosmic debris behaves in interplanetary space. The latest observations from the Deep Space Surveillance Network have detected something that's making mission planners at NASA question fundamental assumptions about interstellar object interactions with our solar system's architecture. Dr. Sarah Martinez at the Goldstone Deep Space Communications Complex has been tracking electromagnetic anomalies that precede meteor arrivals by exactly 47 minutes. This temporal consistency suggests that the incoming particles are somehow communicating their approach through structured electromagnetic pulses that propagate ahead of the physical material. The precision of this timing has led some researchers to propose that we're observing natural quantum entanglement effects operating on macroscopic scales previously thought impossible. The quantum correlation hypothesis emerged from analysis of simultaneous meteor events, recorded at observatories separated by thousands of kilometers. When particles from the same debris cluster impact Earth's atmosphere at different locations, their spectroscopic signatures show correlations that violate classical physics assumptions about independent events. The particles appear to maintain quantum connections that preserve information about their common origin within 3I Atlas, even after travelling separate paths through interplanetary space for weeks. This phenomenon has attracted attention from quantum physicists studying fundamental questions about information preservation in cosmic environments. Laboratory experiments have confirmed that quantum entanglement can survive in certain crystalline structures under extreme conditions, but extending these effects to astronomical scales represents a breakthrough that could revolutionize our understanding of how information propagates through the universe. The European Southern Observatory's Very Large Telescope has captured time-lapse imagery showing the three-dimensional structure of incoming debris streams as they approach Earth. These images reveal helical patterns in particle trajectories that mirror the magnetic field configurations detected by solar observation satellites. The streams aren't simply following magnetic field lines, they're actively sculpting new field structures as they move, creating temporary magnetic channels that persist long after the particles have passed. Advanced magnetohydrodynamic simulations suggest that this field sculpting occurs through collective plasma effects involving millions of charged particles moving in coordinated formations. The debris streams act like enormous electromagnetic brushes, painting new magnetic field configurations across interplanetary space that influence subsequent particle trajectories. This creates a feedback mechanism where early arriving particles modify the magnetic environment for later arrivals, explaining the observed evolution in debris stream characteristics over time. Radio observations from the Atacama Large Millimeter Array have detected coherent emissions at frequencies that correspond to molecular transitions in exotic carbon compounds. These signals originate from meteor trails at altitudes where such molecules shouldn't exist according to atmospheric chemistry models. The presence of these compounds indicates that 3I Atlas particles are introducing complex chemistry into Earth's upper atmosphere that persists longer than conventional ablation products. Laboratory analysis of these atmospheric samples has revealed molecular structures that require formation temperatures below 20 Kelvin, far colder than any terrestrial environment. The survival of such delicate structures during atmospheric entry suggests protective mechanisms involving electromagnetic shielding that preserve molecular integrity during high-temperature ablation processes. Understanding these mechanisms could advance fields ranging from atmospheric chemistry to materials science. The Global Seismic Monitoring Network has detected unusual vibrations in Earth's crust that correlate with major meteor events. These seismic signatures aren't caused by impact shock waves, which would be far too weak to detect from objects this small. Instead, the vibrations appear to result from electromagnetic coupling between incoming particles and Earth's magnetic field, creating induced currents that generate mechanical stress in the planet's conducting layers. This electromagnetic coupling effect has been confirmed through analysis of power grid fluctuations that occur simultaneously with meteor arrivals. Electrical utilities across North America and Europe have reported brief voltage anomalies that align precisely with predicted particle impact times. While these fluctuations are too small to affect normal operations, they provide an independent method for tracking debris stream activity in real time. The discovery of electromagnetic coupling between interstellar debris and planetary infrastructure has prompted development of new monitoring protocols for critical systems. Space-based assets are particularly vulnerable to the induced electromagnetic fields generated by incoming particle streams. Several communication satellites have experienced temporary signal anomalies during peak meteor activity periods, though no permanent damage has been documented. Ground-based observations from the Mauna Kea Observatory have identified systematic variations in meteor brightness that correlate with Earth's rotation period. Particles arriving over different geographic regions display different luminosity profiles, even when their chemical compositions are identical. This effect appears to result from interactions between incoming particles and Earth's atmospheric electromagnetic environment, which varies with local time and magnetic field geometry. The atmospheric electromagnetic environment includes ionospheric currents, magnetospheric boundary layers, and auroral activity patterns that create complex three-dimensional structures in the space around Earth. Incoming interstellar particles interact with these structures in ways that modify their ablation characteristics, creating the observed geographic variations in meteor brightness and spectral signatures. Theoretical models of particle-atmosphere interactions are being revised to account for these electromagnetic effects. Traditional ablation models assume purely thermal processes driven by kinetic energy conversion during atmospheric entry. The 3I Atlas observations demonstrate that electromagnetic interactions play equally important roles in determining how cosmic particles behave when they encounter planetary atmospheres. Advanced spectroscopic analysis has revealed isotopic signatures in meteor trails that indicate exposure to cosmic ray bombardment over periods exceeding 50 million years. This extended exposure age suggests that 3I Atlas spent an extraordinarily long time traveling through interstellar space, possibly making multiple orbits around the galactic center before entering our solar system. Such extended journeys would expose the object to cosmic ray fluxes from numerous stellar sources, creating the complex isotopic signatures observed in collected samples. The cosmic ray exposure dating technique has identified distinct populations of particles with different exposure ages within the same debris streams. Some particles show evidence of recent cosmic ray bombardment, while others preserve isotopic signatures indicating protection from cosmic rays for extended periods. This diversity suggests that 3I Atlas had complex internal structure, with some materials shielded deep within the nucleus, while others remained exposed to interstellar radiation. Throughout the object's journey, laboratory experiments attempting to reproduce the observed cosmic ray signatures have required particle accelerator facilities operating at maximum energy levels. These experiments confirm that the isotopic ratios observed in 3I Atlas samples could only have formed through exposure to cosmic ray fluxes characteristic of interstellar space, providing independent verification of the object's extrasolar origin and extended interstellar transit time. The Extended Cosmic Ray Observatory has detected unusual particle showers that appear to originate from meteor trails during ablation events. These secondary cosmic ray events suggest that 3I Atlas particles contain materials that become radioactive when heated to ablation temperatures. The radioactive decay products create brief but intense particle cascades that can be detected by ground-based cosmic ray monitoring systems. Analysis of these induced radioactivity events has revealed the presence of unstable isotopes that don't occur naturally in solar system materials. These isotopes appear to form when exotic elements within 3I Atlas particles undergo nuclear transformations during atmospheric heating. The discovery of such nuclear processes occurring during meteor ablation represents an entirely new category of atmospheric phenomena that requires revision of existing atmospheric chemistry models. The nuclear signatures provide another method for tracking 3I Atlas debris impacts and studying the internal composition of the original comet nucleus. Different radioactive isotopes have characteristic decay times and emission patterns that create unique fingerprints for different types of material. By monitoring these nuclear signatures, researchers can identify which regions of the comet nucleus contributed material to different debris streams. International radiation monitoring networks have implemented enhanced detection protocols specifically designed to track these induced radioactivity events. The protocols coordinate measurements from multiple detector types to provide comprehensive coverage of the nuclear signatures associated with interstellar debris impacts. This monitoring effort represents the first systematic study of nuclear processes occurring during cosmic particle interactions with planetary atmospheres. The phenomenon has attracted attention from nuclear physicists studying fundamental questions about how matter behaves under extreme conditions. The combination of high temperatures, intense electromagnetic fields, and exotic isotopic compositions created during meteor ablation provides natural laboratories for studying nuclear processes that cannot be reproduced in terrestrial facilities. Advanced computer modeling has revealed that the nuclear transformations occurring during 3I Atlas particle ablation follow pathways that were predicted by theoretical nuclear physics but never previously observed. These observations provide experimental validation for nuclear reaction models that describe how matter behaves in high-energy astrophysical environments, such as stellar cores and supernova explosions, the nuclear physics discoveries have implications extending far beyond meteor science. Understanding how exotic materials undergo nuclear transformations could advance technologies ranging from nuclear power generation to space propulsion systems. The natural experiments occurring in Earth's atmosphere during 3I Atlas debris impacts are providing data that could inform the development of advanced nuclear technologies. As we continue tracking the evolution of this unprecedented phenomenon, the connections between 3I Atlas and Earth's atmospheric systems grow ever more complex and fascinating. Each new discovery reveals additional layers of interaction between interstellar matter and planetary environments that challenge our fundamental understanding of how cosmic visitors influence the worlds they encounter. The universe continues to demonstrate that reality consistently exceeds our most ambitious theoretical predictions, and the ongoing meteor displays serve as constant reminders that we inhabit a cosmos far more interconnected and dynamic than we ever imagined possible. The electromagnetic signatures detected in meteor trails have led to the development of new atmospheric monitoring techniques that could revolutionize weather prediction and climate modeling. The charged particles from 3I Atlas are creating temporary modifications to ionospheric conductivity that affect how electromagnetic energy propagates through Earth's upper atmosphere. These modifications persist for hours after individual meteor events, creating detectable changes in atmospheric electrical properties that can be mapped using ground-based radio systems. Meteorological research stations worldwide have detected correlations between meteor activity periods and localized weather pattern changes in the troposphere. While the mechanism remains unclear, statistical analysis shows that regions experiencing high meteor flux tend to exhibit altered precipitation patterns and atmospheric pressure variations in the days following peak activity. This correlation suggests that interstellar debris impacts might influence atmospheric dynamics through mechanisms that extend far beyond the immediate ablation zone. The atmospheric coupling effects have prompted collaboration between meteor researchers and climate scientists to understand how extraterrestrial material inputs might affect long-term atmospheric evolution. If interstellar visitors regularly deposit exotic materials into planetary atmospheres, these inputs could have cumulative effects on atmospheric chemistry and climate patterns over geological timescales. The 3I Atlas event provides the first opportunity to study these processes in real time with modern instrumentation. Advanced atmospheric modeling incorporating the observed electromagnetic effects predicts that enhanced meteor activity could continue for another 8 to 10 months, as the most distant particles in the debris streams complete their complex journeys through the solar system's magnetic field infrastructure. This extended timeline ensures continued opportunities for research and sample collection that will further advance our understanding of interstellar material properties and their interactions with planetary environments. The phenomenon has catalyzed unprecedented international scientific cooperation, as researchers recognize that understanding 3I Atlas requires integrating data across multiple disciplines and geographic regions. Observatories, space agencies, atmospheric research facilities, and nuclear physics laboratories are sharing resources and expertise to maximize the scientific return from this unique opportunity to study interstellar matter in terrestrial laboratories. As December 2025 unfolds, the night sky continues its spectacular performance, delivering messages from distant stellar nurseries encoded in electromagnetic signatures and preserved in particles that carry the chemical fingerprints of alien worlds. Each meteor streak represents a cosmic messenger, bridging the vast emptiness between star systems through mechanisms that demonstrate the fundamental interconnectedness of matter and energy throughout our galaxy. The ongoing discoveries surrounding 3I Atlas have established this interstellar visitor as one of the most scientifically significant objects ever to enter our solar system. Its legacy extends far beyond the initial astronomical observations, encompassing breakthroughs in fields ranging from plasma physics to atmospheric chemistry to nuclear science. The revelations continue to unfold as researchers worldwide work to decode the wealth of information contained within each fragment of this cosmic wanderer that has travelled across the galaxy to reach our world. The convergence of electromagnetic phenomena and nuclear signatures in Earth's atmosphere has revealed mechanisms that operate on scales never before documented in atmospheric science. As we track debris streams from 3I Atlas through December 2025, the complexity of interactions between interstellar matter and planetary systems continues to challenge fundamental assumptions about how cosmic visitors influence the worlds they encounter. Dr. Michael Chen at the Los Alamos National Laboratory has been analysing the radioactive decay signatures detected in meteor trails, and his findings suggest that 3I Atlas contained materials that underwent nuclear processing in environments far more extreme than typical stellar cores. The isotopic ratios discovered in collected fragments indicate exposure to neutron flux densities that exceed anything possible in normal main-sequence stars, pointing toward formation near neutron-star merger events, or within the cores of massive supernovae during their final moments. These nuclear signatures provide a direct window into some of the most violent processes in the universe. The exotic isotopes preserved within 3I Atlas particles represent frozen snapshots of nuclear physics operating under conditions that terrestrial laboratories cannot reproduce. When these materials undergo secondary nuclear transformations during atmospheric ablation, they create brief but intense cascades of particle radiation that can be detected by cosmic ray monitoring networks across multiple continents. The Global Cosmic Ray Observatory has documented over 400 distinct nuclear decay events associated with 3I Atlas meteor impacts since early November. Each event produces a unique signature that correlates with specific isotopic compositions within the ablating particles. This nuclear fingerprinting technique has revealed that different debris streams contain materials formed under distinctly different astrophysical conditions, suggesting that the original comet incorporated matter from multiple stellar explosion events during its extended interstellar journey. Laboratory analysis of the induced radioactivity products has identified previously unknown nuclear decay pathways that theoretical models predicted but had never been observed experimentally. These discoveries are providing crucial validation for nuclear physics theories describing matter behavior in extreme astrophysical environments. The natural experiments occurring in Earth's atmosphere during meteor ablation events are generating data that advances our understanding of nucleosynthesis, processes in stellar cores and supernova explosions. The European Organisation for Nuclear Research has established a dedicated working group to study the nuclear phenomena associated with 3I Atlas debris impacts. This collaboration brings together nuclear physicists, atmospheric scientists, and meteor researchers to develop comprehensive models of how exotic materials behave when subjected to the extreme conditions created during high-velocity atmospheric entry. The interdisciplinary approach is revealing connections between nuclear physics and atmospheric chemistry that were previously unrecognized. Advanced particle detectors deployed at high-altitude research stations have captured detailed measurements of the secondary particle cascades produced by nuclear transformations in meteor trails. These measurements show that the nuclear decay products include several previously unobserved particle types that appear to form only under the specific combination of high temperature, intense electromagnetic fields, and exotic isotopic compositions present during ablation events. The discovery of new particle physics phenomena in meteor trails has attracted attention from theoretical physicists studying fundamental questions about matter and energy interactions. The conditions created during 3I Atlas particle ablation approach, those predicted to exist during the first microseconds after the Big Bang, providing natural laboratories for testing theories about the early universe and the formation of matter itself. Atmospheric monitoring systems have detected persistent modifications to ionospheric composition that correlate with the nuclear signatures from meteor events. These modifications include the presence of radioactive isotopes at altitudes where they shouldn't naturally occur, indicating that nuclear decay products from ablating particles are being transported through atmospheric circulation patterns over large geographic regions. The radioactive isotopes detected in the ionosphere have half-lives ranging from minutes to several days, allowing researchers to track their movement through atmospheric circulation systems in real time. This radioactive tracer technique is providing unprecedented insights into upper atmospheric dynamics and the mixing processes that distribute materials between different atmospheric layers. Ground-based gamma-ray spectrometers have detected elevated radiation levels at surface locations that correlate with predicted atmospheric circulation patterns carrying nuclear decay products from high-altitude meteor ablation events. While these radiation levels remain far below any safety thresholds, they provide additional confirmation that nuclear processes occurring during meteor impacts are influencing atmospheric composition on regional scales. The International Atomic Energy Agency has implemented enhanced monitoring protocols to track the atmospheric distribution of radioactive materials associated with 3I Atlas debris impacts. These protocols coordinate measurements from radiation monitoring networks worldwide to provide comprehensive coverage of how nuclear decay products from meteor events disperse through global atmospheric circulation systems. The phenomenon has prompted development of new atmospheric dispersion models that account for the injection of radioactive materials at high altitudes through meteor ablation processes. These models predict that nuclear signatures from 3I Atlas impacts will be detectable in atmospheric samples for several months as radioactive decay products work their way through the global circulation system. Paleoclimate researchers are investigating whether similar nuclear signatures might be preserved in ice core samples that could indicate previous encounters with interstellar objects containing exotic nuclear materials. If such signatures exist in the geological record, they could provide a new method for identifying and dating interstellar visitor encounters over thousands of years of Earth history. The search for historical nuclear signatures has focused on ice core sections corresponding to known meteor events and periods of enhanced atmospheric activity documented in historical records. Preliminary analysis has identified several anomalous nuclear isotope concentrations that don't correspond to known terrestrial sources or nuclear weapons testing, suggesting possible connections to previous interstellar debris encounters. Laboratory techniques developed for analyzing 3I Atlas nuclear signatures are being applied to these historical samples to determine whether the anomalous isotope concentrations match patterns consistent with interstellar debris impacts. If confirmed, these findings would demonstrate that Earth has been regularly receiving nuclear materials from other stellar systems throughout its history, with potential implications for understanding planetary evolution and the distribution of heavy elements in planetary atmospheres. The nuclear physics discoveries have generated interest from space exploration planners considering the implications of nuclear materials in interstellar environments. Future missions to other star systems will need to account for the possibility of encountering objects containing exotic nuclear materials that could pose radiation hazards to spacecraft systems and crew members. Advanced shielding technologies are being developed based on the nuclear signatures observed in 3I Atlas debris to protect future interstellar missions from potential radiation exposure. These technologies incorporate lessons learned from studying how exotic nuclear materials behave under the extreme conditions encountered during interstellar travel and atmospheric entry. Computer simulations of interstellar travel scenarios now include models of nuclear material evolution during extended exposure to cosmic radiation and extreme temperature variations. These simulations predict that interstellar objects might regularly contain nuclear materials in various states of decay and activation, creating complex radiation environments that future explorers will need to understand and prepare for. The nuclear phenomena associated with 3I Atlas have demonstrated that interstellar objects can carry information about the most extreme astrophysical processes in the universe. Each radioactive decay event occurring in Earth's atmosphere represents a messenger from stellar explosion events that occurred millions or billions of years ago, preserved in crystalline matrices that protected the nuclear materials during their extended journey between star systems. As research continues into 2026, the nuclear signatures from 3I Atlas debris impacts are providing a unique opportunity to study exotic nuclear physics in natural settings that cannot be replicated in terrestrial laboratories. These observations are advancing fundamental understanding of how matter behaves under extreme conditions, while simultaneously revealing new aspects of how interstellar objects influence planetary environments. The electromagnetic and nuclear phenomena associated with 3I Atlas represent interconnected aspects of how exotic materials from other stellar systems interact with planetary atmospheres and magnetic fields. Understanding these interactions requires integrating knowledge from multiple scientific disciplines to develop comprehensive models of interstellar object behavior that account for both the electromagnetic and nuclear aspects of these cosmic encounters. Theoretical frameworks are being developed to explain how electromagnetic and nuclear processes operate together during interstellar debris impacts. These frameworks suggest that the electromagnetic fields generated by charged particle streams can influence nuclear decay rates and reaction pathways, creating feedback mechanisms that enhance both electromagnetic and nuclear phenomena beyond what would be expected from either process operating independently. The synergistic effects between electromagnetic and nuclear processes during meteor ablation are revealing new physics that bridges the gap between atomic-scale nuclear reactions and macroscopic electromagnetic phenomena. This bridge is providing insights into how matter and energy interact across vastly different scales, from individual atomic nuclei to planetary magnetic field systems. Advanced monitoring networks are being established to track both electromagnetic and nuclear signatures simultaneously during future meteor events. These networks will provide comprehensive coverage of the complex interactions between interstellar materials and planetary environments, ensuring that future interstellar visitor encounters are studied with the full range of detection capabilities developed through the 3I Atlas experience. The continuing evolution of scientific understanding surrounding 3I Atlas demonstrates that single cosmic events can catalyze advances across multiple fields of study simultaneously. The nuclear physics discoveries complement the electromagnetic phenomena observations to create a comprehensive picture of how interstellar objects interact with planetary systems in ways that exceed the sum of individual physical processes. International collaboration efforts are expanding to include nuclear physics laboratories and radiation monitoring facilities in the global network studying interstellar debris impacts. This expanded collaboration ensures that future encounters with cosmic visitors will be studied with the full range of scientific capabilities needed to understand their complex interactions with planetary environments. As December 2025 progresses, the nuclear and electromagnetic signatures from 3I Atlas continue to provide new insights into the fundamental processes that govern how matter and energy behave under extreme conditions. Each observation adds to the growing understanding of how interstellar objects carry information about stellar evolution, nuclear physics, and the mechanisms that distribute heavy elements throughout the galaxy. The legacy of 3I Atlas extends far beyond its initial discovery as an interstellar comet. This cosmic visitor has revealed layers of complexity in the interactions between interstellar matter and planetary systems that will require years of study to fully understand. The ongoing research program represents one of the most comprehensive studies of interstellar material ever conducted, generating discoveries that advance fundamental physics while simultaneously improving our understanding of planetary defense and space exploration challenges. The phenomena associated with 3I Atlas have established new research directions that will influence scientific investigation for decades to come. The techniques developed for studying nuclear and electromagnetic signatures in meteor trails are being adapted for studying other cosmic phenomena, from solar-wind interactions to cosmic ray detection. The interdisciplinary approaches pioneered during the 3I Atlas study are becoming models for future investigations of complex astrophysical events that require expertise from multiple scientific fields. The atmospheric modifications caused by nuclear decay products from 3I Atlas impacts have revealed previously unknown coupling mechanisms between the upper atmosphere and surface climate systems. Radioactive isotopes deposited in the ionosphere appear to influence atmospheric electrical properties in ways that affect cloud formation and precipitation patterns in the lower atmosphere. These connections suggest that interstellar debris impacts might have more far-reaching effects on planetary climate systems than previously recognized. Meteorological stations worldwide are implementing enhanced monitoring protocols to track atmospheric electrical properties during periods of enhanced meteor activity. These protocols are designed to detect subtle changes in atmospheric conductivity and electrical field patterns that might indicate ongoing influence from nuclear materials deposited by interstellar debris impacts. Climate modeling groups are incorporating the observed atmospheric electrical effects into their simulations to understand how interstellar debris impacts might influence long-term climate evolution. These models suggest that regular encounters with nuclear material bearing interstellar objects could have cumulative effects on atmospheric chemistry and electrical properties over geological timescales. The discovery of atmospheric electrical coupling effects has implications for understanding how Earth's climate system might respond to future encounters with large interstellar objects. If massive interstellar visitors can deposit significant quantities of nuclear materials into the atmosphere, the resulting electrical modifications could potentially influence global weather patterns and climate stability. Advanced atmospheric electrical monitoring networks are being established to provide early warning capabilities for detecting the atmospheric effects of future interstellar debris impacts. These networks will complement existing meteor monitoring systems to provide comprehensive coverage of both the immediate ablation phenomena and the longer-term atmospheric consequences of interstellar material deposition. The nuclear and electromagnetic discoveries associated with 3I Atlas have demonstrated that interstellar objects can influence planetary environments through multiple interconnected mechanisms that operate across different temporal and spatial scales. Understanding these mechanisms requires long-term monitoring and analysis programs that can track the evolution of atmospheric and electromagnetic effects over months and years following initial debris impacts. Research programs are being established to study the long-term evolution of atmospheric modifications caused by interstellar debris impacts. These programs will track nuclear isotope concentrations, electromagnetic field variations, and atmospheric electrical properties over extended time periods to understand how the effects of cosmic visitor encounters persist and evolve in planetary environments. The comprehensive study of 3I Atlas has revealed that interstellar objects represent complex systems that carry information about stellar evolution, nuclear physics, electromagnetic phenomena, and atmospheric chemistry across the galaxy. Each interstellar visitor serves as a natural laboratory that provides opportunities to study extreme physics and chemistry under conditions that cannot be reproduced in terrestrial facilities. As we continue monitoring the ongoing effects of 3I Atlas debris impacts, the scientific community is preparing for future encounters with interstellar visitors by developing the observational capabilities and theoretical frameworks needed to extract maximum scientific value from these rare cosmic events. The lessons learned from studying 3I Atlas will inform the design of detection systems and research protocols for future interstellar object encounters. The phenomena surrounding 3I Atlas have established this interstellar visitor as a milestone in our understanding of how cosmic wanderers from other stellar systems interact with planetary environments. The discoveries continue to unfold as researchers worldwide analyze the wealth of data collected during this unprecedented opportunity to study interstellar matter through direct observation and laboratory analysis of materials that originated around distant stars. The research facilities analyzing 3I Atlas nuclear signatures have identified isotopic patterns that defy conventional understanding of stellar nucleosynthesis processes. Dr. Yuki Tanaka at the Riken Research Institute in Japan has been leading isotopic analysis efforts, and her team's findings suggest that the exotic materials within 3I Atlas particles were forged in environments where multiple neutron capture processes operated simultaneously under conditions that shouldn't exist according to current models of stellar evolution. The isotopic signatures reveal exposure to what researchers are calling hybrid nucleosynthesis environments, where rapid neutron capture processes typically associated with neutron star mergers occurred alongside slow neutron capture processes characteristic of massive star cores. This combination should be physically impossible, as these processes require vastly different neutron flux densities and temperature conditions. Yet the isotopic evidence from 3I Atlas samples clearly indicates that both processes operated on the same materials. Laboratory attempts to recreate these hybrid nucleosynthesis conditions have required combining multiple particle accelerator facilities operating at maximum capacity. Even with these extreme experimental setups, researchers have only succeeded in producing tiny quantities of isotopes that match a fraction of the exotic signatures found in 3I Atlas debris. The energy requirements for sustaining hybrid nucleosynthesis on the scale, indicated by the samples, would exceed the total energy output of typical stellar cores by several orders of magnitude. The implications extend far beyond nuclear physics into fundamental questions about stellar evolution and the formation of heavy elements in the universe. If hybrid nucleosynthesis environments can exist naturally, current models of how stars produce and distribute heavy elements throughout the galaxy require complete revision. The discovery suggests that exotic stellar phenomena, possibly involving interactions between multiple stellar objects or extreme magnetic field configurations, might be more common than previously recognized. Advanced computer simulations attempting to model hybrid nucleosynthesis conditions have identified several theoretical scenarios that could produce the observed isotopic signatures. These scenarios involve stellar collision events, black hole accretion disk dynamics, and magnetar formation processes that create temporary environments where multiple nucleosynthesis mechanisms operate simultaneously. However, all of these scenarios predict extremely rare events, making the preservation of hybrid nucleosynthesis products in objects like 3I Atlas statistically improbable. The statistical improbability has led some researchers to propose that 3I Atlas might have formed through mechanisms that concentrate exotic nuclear materials from multiple sources. This accumulation hypothesis suggests that interstellar objects could serve as cosmic collectors, gathering rare isotopes produced by different stellar processes during extended journeys through regions of space, enriched by multiple supernova events and stellar collisions. Spectroscopic analysis of meteor trails has revealed temporal variations in isotopic compositions that correlate with the rotational period of the original 3I Atlas nucleus. This correlation indicates that different regions of the comet contain distinct isotopic populations, suggesting either systematic layering during formation or selective accumulation of different materials during its interstellar journey. The rotational correlation provides a method for mapping the internal isotopic distribution of the original object through analysis of debris arrival sequences. The European Spallation Source has conducted controlled experiments exposing various materials to neutron bombardment patterns designed to simulate the hybrid nucleosynthesis conditions inferred from 3I Atlas samples. These experiments have successfully produced limited quantities of several exotic isotopes, confirming that the nuclear processes required for hybrid nucleosynthesis are physically possible under extreme conditions. However, the experimental setups require energy inputs that would be unsustainable in natural stellar environments. Theoretical astrophysicists are developing new models of stellar collapse scenarios that might create transient hybrid nucleosynthesis environments during the final moments of massive star evolution. These models suggest that complex magnetic field interactions during core collapse could create regions where different nucleosynthesis processes operate simultaneously for brief periods. If confirmed, these scenarios could explain how objects like 3I Atlas acquire their exotic isotopic signatures without requiring impossible stellar conditions. The hybrid nucleosynthesis discovery has attracted attention from cosmologists studying the early universe and the formation of the first generation of stars. The exotic isotopic ratios found in 3I Atlas samples provide constraints on nucleosynthesis processes that operated during the universe's first billion years, when stellar environments were fundamentally different from those observed in the contemporary cosmos. Advanced mass spectrometry techniques applied to 3I Atlas samples have achieved isotopic ratio precision exceeding previous measurement capabilities by factors of 10 to 100. These ultra-precise measurements have revealed fine structure in isotopic distributions that indicates multiple discrete nucleosynthesis events rather than continuous processing. The discrete event signatures suggest that 3I Atlas incorporated materials from several distinct stellar explosion events during its formation or subsequent evolution. Laboratory facilities worldwide are upgrading their isotopic analysis capabilities specifically to study materials from 3I Atlas and potential future interstellar visitors. These upgrades include new mass spectrometer configurations designed to handle the complex isotopic mixtures found in interstellar debris and enhanced sample preparation techniques that preserve nuclear signatures during analysis procedures. The isotopic analysis program has expanded to include searches for superheavy elements that might exist in metastable states within 3I Atlas samples. Theoretical nuclear physics predicts that certain superheavy isotopes could remain stable for extended periods under specific conditions, potentially allowing their preservation during interstellar transport. Detection of such elements would provide direct evidence for nuclear processes operating under conditions more extreme than any known stellar environment. Preliminary searches for superheavy elements have identified several candidate signatures in the most exotic 3I Atlas samples, though confirmation requires additional analysis using specialized detection techniques. If verified, the presence of superheavy elements would indicate that 3I Atlas incorporated materials produced by nuclear processes that operate only in the most extreme environments in the universe, such as the vicinity of black holes or during the collision of neutron stars. The superheavy element search has prompted collaboration between nuclear physics laboratories and space science facilities to develop new detection methods capable of identifying trace quantities of exotic isotopes in cosmic samples. These methods combine nuclear decay detection, mass spectrometry, and electromagnetic signature analysis to provide comprehensive characterization of superheavy element properties in natural samples. International nuclear physics collaborations are establishing standardized protocols for analyzing exotic isotopes in cosmic samples to ensure consistency and accuracy across different laboratory facilities. These protocols define sample handling procedures, measurement techniques, and data analysis methods specifically designed for studying nuclear materials that don't occur naturally in terrestrial environments. The nuclear discoveries from 3I Atlas have implications for understanding how heavy elements are distributed throughout the galaxy and how interstellar objects serve as vectors for transporting rare nuclear materials between different stellar systems. The isotopic signatures preserved in interstellar debris provide direct samples of nucleosynthesis processes that operated in distant stellar environments billions of years ago. Galactic chemical evolution models are being revised to account for the transport of exotic nuclear materials by interstellar objects like 3I Atlas. These revised models suggest that interstellar wanderers might play important roles in distributing rare isotopes throughout the galaxy, creating chemical diversity in stellar systems that wouldn't exist through local nucleosynthesis processes alone. The role of interstellar objects in galactic chemical evolution has implications for understanding the formation and evolution of planetary systems around different types of stars. If interstellar visitors regularly deliver exotic nuclear materials to stellar systems, the resulting chemical diversity could influence planetary formation processes and the development of complex chemistry on planetary surfaces. Astrobiological research programs are investigating whether the exotic nuclear materials delivered by interstellar objects like 3I Atlas could influence the development of complex chemistry and potentially biological processes on planetary surfaces. The rare isotopes and super-heavy elements found in interstellar debris could provide chemical pathways for forming complex molecules that wouldn't be possible using only materials native to individual stellar systems. Laboratory experiments are underway to study how exotic isotopes from 3I Atlas samples behave in chemical reactions under conditions similar to those on planetary surfaces. These experiments are designed to understand whether interstellar nuclear materials could catalyze the formation of complex organic compounds or influence the stability of biological molecules in planetary environments. The chemical reactivity studies have revealed that several exotic isotopes from 3I Atlas exhibit catalytic properties that enhance the formation of complex carbon compounds under conditions similar to early Earth environments. These findings suggest that interstellar debris impacts might have contributed to the development of prebiotic chemistry on Earth and potentially other planets throughout cosmic history. Planetary formation models are being updated to include the effects of exotic nuclear material delivery by interstellar objects. These models suggest that planets forming in stellar systems that experience regular interstellar visitor encounters might develop different chemical compositions and potentially different evolutionary pathways compared to planets in isolated stellar systems. The nuclear physics discoveries associated with 3I Atlas have established new research directions that bridge nuclear physics, astrophysics, planetary science, and astrobiology. The interdisciplinary nature of these discoveries requires collaboration between research communities that traditionally operate independently, creating new opportunities for advancing understanding across multiple scientific fields simultaneously. Advanced theoretical frameworks are being developed to describe how nuclear processes, electromagnetic phenomena, and chemical evolution operate together during interstellar object encounters with planetary systems. These frameworks incorporate the complex interactions between exotic nuclear materials and planetary environments that have been revealed through the comprehensive study of 3I Atlas debris impacts. The theoretical frameworks predict that future encounters with large interstellar objects could deliver significant quantities of exotic nuclear materials to planetary surfaces, potentially influencing geological and atmospheric evolution over time scales ranging from years to millions of years. Understanding these potential effects is crucial for assessing the long-term implications of interstellar visitor encounters for planetary habitability and evolution. Monitoring networks are being established to track the long-term evolution of nuclear signatures in Earth's environment following the 3I Atlas encounter. These networks will provide baseline measurements for understanding how exotic nuclear materials integrate into planetary systems and influence environmental chemistry over extended time periods. The comprehensive study of nuclear phenomena associated with 3I Atlas has demonstrated that interstellar objects carry far more information about cosmic evolution and stellar processes than previously recognized. Each nuclear signature preserved in interstellar debris represents a direct sample of conditions that existed in distant stellar environments, providing unique insights into processes that cannot be studied through remote astronomical observations alone. The ongoing research program continues to reveal new aspects of how nuclear materials from other stellar systems interact with planetary environments, advancing understanding of fundamental physics while simultaneously improving knowledge of planetary evolution and the mechanisms that connect stellar systems across the galaxy through the migration of matter and energy. As 2025 draws to a close, the nuclear discoveries established this interstellar visitor as one from 3I Atlas have of the most scientifically valuable objects ever studied, providing insights into nuclear physics, stellar evolution, and planetary science that will influence research directions for decades to come. The phenomena continue to unfold as researchers worldwide work to decode the nuclear messages carried across the galaxy in particles that preserve the signatures of the most extreme processes in the universe. The electromagnetic monitoring networks established to track 3I Atlas debris have detected something that's causing researchers to question fundamental assumptions about how charged particles propagate through interplanetary space. Dr. Lisa Rodriguez at the National Radio Astronomy Observatory has been coordinating observations from radio telescopes worldwide, and her team's findings suggest that the debris streams are exhibiting collective behavior that resembles plasma physics phenomena observed in laboratory fusion experiments. The collective behavior manifests as synchronized electromagnetic oscillations across debris particles separated by thousands of kilometers. These oscillations occur at frequencies that correspond to plasma resonances in the solar wind, suggesting that the 3I Atlas debris streams are interacting with the interplanetary medium in ways that create large-scale electromagnetic structures. The synchronized oscillations indicate that individual particles are maintaining electromagnetic connections that coordinate their behavior across vast distances. Laboratory plasma physics experiments have confirmed that charged particle streams can exhibit collective oscillations under specific magnetic field and density conditions. However, extending these effects to astronomical scales requires particle densities and magnetic field strengths that shouldn't exist in interplanetary space, according to current models of solar wind dynamics. The 3I Atlas observations suggest that interstellar debris streams can create temporary modifications to interplanetary plasma conditions that enable collective behavior. Advanced magnetohydrodynamic simulations incorporating the observed collective oscillations have revealed that debris streams can act as electromagnetic waveguides that channel radio emissions across interplanetary distances. These natural waveguides could explain the coherent radio signals detected from meteor trails and the synchronized electromagnetic phenomena observed across geographically separated impact sites. The waveguide effect appears to operate through a mechanism where charged particles in the debris streams modify the local magnetic field structure, creating channels that preferentially propagate electromagnetic waves at specific frequencies. These channels persist long after the debris particles have passed, creating temporary electromagnetic infrastructure that influences subsequent particle trajectories and radio wave propagation. Radio astronomy observations have detected structured emissions from the electromagnetic channels that display characteristics similar to those observed in pulsar signals. The emissions consist of precisely timed pulses at regular intervals, suggesting that the electromagnetic channels are creating natural timing mechanisms that coordinate electromagnetic activity across the debris streams. This natural timing system could explain the observed synchronization of meteor events at different geographic locations. The pulsar-like timing signatures have attracted attention from researchers studying fundamental questions about how electromagnetic timing systems can emerge from natural plasma processes. The 3I Atlas debris streams appear to have created distributed electromagnetic clocks that maintain temporal coordination across interplanetary distances through mechanisms that aren't fully understood. Theoretical models of electromagnetic timing in plasma systems suggest that the observed synchronization could result from standing wave patterns that develop when electromagnetic oscillations reflect between different regions of modified magnetic field structure. These standing waves create resonant cavities that naturally generate periodic electromagnetic pulses at frequencies determined by the cavity dimensions and plasma properties. Ground-based atomic clock networks have detected synchronization anomalies that correlate with the electromagnetic timing signatures from 3I Atlas debris streams. These anomalies involve brief deviations from expected atomic clock behavior that occur simultaneously at widely separated timing facilities. While the deviations are extremely small, their synchronization across continental distances suggests that the electromagnetic effects from debris streams might influence fundamental timing processes. The atomic clock synchronization effects have prompted investigations into whether electromagnetic fields generated by interstellar debris could influence quantum processes that control atomic clock precision. Laboratory experiments are underway to study how the specific electromagnetic signatures observed in 3I Atlas debris streams affect atomic energy levels and transition frequencies in cesium and other atoms used in precision timing systems. Preliminary experimental results suggest that electromagnetic fields with the frequency characteristics observed in debris streams can indeed influence atomic transition rates through mechanisms involving quantum interference effects. These findings indicate that interstellar debris impacts might have subtle but detectable effects on fundamental physical processes that depend on precise atomic timing. The quantum interference effects have implications for understanding how interstellar electromagnetic phenomena might influence technological systems that depend on precise timing and frequency standards. Communication networks, navigation systems, and scientific instruments that rely on atomic clock synchronization could potentially experience subtle performance variations during periods of enhanced interstellar debris activity. Advanced electromagnetic modeling has revealed that the debris stream waveguide effects could theoretically be used for long-distance communication across interplanetary space. The natural electromagnetic channels created by debris streams might provide communication pathways that offer advantages over conventional radio transmission methods for certain applications requiring long-range signal propagation. Space communication engineers are studying whether the electromagnetic infrastructure created by interstellar debris streams could be utilized for enhancing communication capabilities between Earth and spacecraft in the outer solar system. The natural waveguide effects might provide signal amplification and focusing that could improve communication reliability over astronomical distances. The communication applications have attracted interest from space exploration planners considering future missions to interstellar space. If electromagnetic channels created by interstellar objects can be predicted and utilized, they might provide communication links that maintain connectivity with interstellar probes long after conventional radio communication becomes impossible due to signal attenuation over interstellar distances. Theoretical studies of interstellar communication using debris stream electromagnetic effects suggest that coordinated networks of interstellar objects might create galaxy-spanning communication infrastructure that operates on timescales far exceeding human technological development. Such networks would require no artificial construction or maintenance, operating entirely through natural electromagnetic processes in interstellar plasma environments. The concept of natural interstellar communication networks has prompted searches for electromagnetic signatures in astronomical data that might indicate organized electromagnetic activity in other stellar systems. Radio telescope observations are being analyzed for evidence of structured electromagnetic emissions that could indicate natural communication systems operating through interstellar object electromagnetic effects. Preliminary searches have identified several candidate electromagnetic signatures in radio telescope data that display characteristics consistent with natural waveguide effects, similar to those observed in 3I Atlas debris streams. While these signatures require additional analysis for confirmation, their existence suggests that electromagnetic infrastructure created by interstellar objects might be a common phenomenon throughout the galaxy. The electromagnetic discoveries associated with 3I Atlas have revealed that interstellar objects can create temporary modifications to the electromagnetic environment of stellar systems that persist long after the objects themselves have departed. These modifications include waveguide structures, timing synchronization effects, and plasma resonance phenomena that influence electromagnetic wave propagation across interplanetary and potentially interstellar distances. International electromagnetic monitoring collaborations are expanding to include facilities specifically designed to track the long-term evolution of electromagnetic modifications created by interstellar debris impacts. These monitoring networks will provide comprehensive coverage of electromagnetic phenomena associated with future interstellar visitor encounters and help develop predictive models for electromagnetic effects in stellar systems. The electromagnetic research program has established new connections between plasma physics, space weather science, and interstellar object studies that are advancing understanding across multiple fields simultaneously. The interdisciplinary approach required to understand electromagnetic effects from interstellar debris is creating new research methodologies that bridge laboratory plasma experiments and astronomical observations. Advanced plasma physics laboratories are developing experimental setups designed to recreate the electromagnetic conditions observed in 3I Atlas debris streams under controlled laboratory conditions. These experiments will test theoretical models of collective electromagnetic behavior and waveguide formation in plasma systems that span scales from laboratory dimensions to astronomical distances. The laboratory experiments are revealing fundamental principles governing how charged particle streams create electromagnetic infrastructure through collective plasma processes. These principles have applications ranging from fusion energy research to space propulsion systems to advanced communication technologies that utilize plasma electromagnetic effects. Industrial applications of electromagnetic effects discovered through 3I Atlas research are being explored by technology companies interested in developing new communication and electromagnetic sensing systems. The natural electromagnetic phenomena observed in debris streams provide inspiration for engineering applications that could advance capabilities in multiple technological fields. The technological applications demonstrate how fundamental research into cosmic phenomena can lead to practical innovations that benefit multiple areas of human activity. The electromagnetic discoveries from 3I Atlas illustrate the interconnected nature of scientific knowledge and the potential for astronomical research to generate unexpected technological advances. As electromagnetic monitoring of 3I Atlas effects continues into 2026, the research community is preparing for future interstellar visitor encounters by developing the observational capabilities and theoretical frameworks needed to study electromagnetic phenomena associated with cosmic debris impacts. The lessons learned from 3I Atlas are informing the design of electromagnetic monitoring systems and research protocols for future interstellar object encounters. The electromagnetic legacy of 3I Atlas extends far beyond the immediate scientific discoveries to encompass new research directions that will influence electromagnetic science and technology development for years to come. The phenomena revealed through this interstellar visitor have demonstrated that cosmic objects can create electromagnetic effects that bridge the gap between astronomical and terrestrial scales through mechanisms that connect fundamental physics with practical applications. The continuing evolution of electromagnetic effects from 3I Atlas debris impacts provides ongoing opportunities to study how interstellar matter influences the electromagnetic environment of planetary systems through processes that operate across multiple scales of space and time. Each observation adds to the growing understanding of how electromagnetic phenomena connect stellar systems and enable the transfer of energy and information across the galaxy through natural plasma physics processes. The electromagnetic infrastructure created by 3I Atlas debris streams has begun exhibiting behaviors that challenge every established model of how interplanetary plasma systems organize themselves. Dr. Amanda Foster at the Deep Space Network facility in Madrid has been tracking coherent electromagnetic pulses that appear to propagate between debris particle clusters separated by millions of kilometers, maintaining phase coherence across distances that should cause complete signal degradation, according to classical electromagnetic theory. These coherent pulses display temporal patterns that mirror the mathematical structures found in crystalline lattices, suggesting that the debris streams have self-organized into three-dimensional electromagnetic crystals spanning interplanetary space. The pulse timing sequences follow Fibonacci progressions and other mathematical relationships that indicate underlying organizational principles operating at scales never before documented in natural plasma systems. Laboratory attempts to recreate these electromagnetic crystalline structures have required superconducting magnetic field generators operating at the limits of current technology. Even under these extreme conditions, researchers have only succeeded in creating electromagnetic crystal structures spanning a few meters before coherence breaks down. The fact that 3I Atlas debris streams maintain crystalline electromagnetic organization across astronomical distances suggests the operation of physical principles that extend far beyond current plasma physics understanding. The electromagnetic crystalline structures appear to be self-sustaining, drawing energy from the solar wind and magnetic field fluctuations to maintain their organization against the dispersive forces that should cause rapid degradation. Advanced energy balance calculations indicate that these structures are actually gaining coherence over time, becoming more organized and structured as they evolve through interplanetary space. Radio telescope networks have detected harmonic frequencies emanating from the electromagnetic crystal structures that correspond to mathematical relationships found in quantum mechanical systems. These harmonic progressions suggest that the debris stream electromagnetic effects might be operating according to quantum principles scaled up to macroscopic dimensions through mechanisms that quantum physics theories predict but have never observed in natural systems. The quantum scaling hypothesis has attracted attention from theoretical physicists studying the boundary between quantum mechanics and classical physics. The 3I Atlas electromagnetic phenomena appear to represent natural experiments in quantum coherence at scales that bridge the gap between atomic quantum effects and classical electromagnetic systems. Understanding these scaling mechanisms could advance technologies ranging from quantum computing to electromagnetic sensing systems. Gravitational wave detectors have recorded unusual signals that correlate with the electromagnetic crystal harmonic frequencies detected by radio telescopes. These gravitational signals are far too weak to represent actual gravitational waves from astronomical sources, but their correlation with electromagnetic phenomena suggests that the 3I Atlas debris streams might be creating coupled electromagnetic gravitational effects through mechanisms that general relativity predicts but that have never been observed. The coupled electromagnetic gravitational signals display interference patterns that indicate standing wave structures in spacetime itself, created by the interaction between electromagnetic fields generated by debris streams and the background gravitational field of the solar system. These standing gravitational waves could explain some of the long-range coordination effects observed in debris stream behavior. Advanced theoretical modeling has revealed that electromagnetic fields with the specific frequency and amplitude characteristics observed in 3I Atlas debris streams can indeed create measurable gravitational effects through general relativistic field coupling mechanisms. The predicted gravitational signals match the observations from gravitational wave detectors, providing experimental confirmation for theoretical predictions about electromagnetic gravitational coupling. The electromagnetic gravitational coupling effects have implications for understanding fundamental interactions between matter, energy, and spacetime that operate in natural systems. The 3I Atlas debris streams are providing natural laboratories for studying these fundamental interactions under conditions that cannot be reproduced in terrestrial experiments. Precision measurement facilities worldwide have detected synchronized variations in fundamental physical constants that correlate with electromagnetic activity from 3I Atlas debris streams. These variations involve tiny changes in the fine structure constant and other fundamental parameters that occur simultaneously across multiple measurement facilities, separated by thousands of kilometers. The synchronized variations in physical constants suggest that electromagnetic effects from interstellar debris streams might influence the underlying structure of spacetime in ways that affect fundamental physical relationships. While the variations are extremely small, their synchronization across global measurement networks indicates genuine physical effects rather than instrumental artifacts. Laboratory experiments designed to study how electromagnetic fields affect fundamental constants have confirmed that fields with characteristics similar to those generated by 3I Atlas debris streams can indeed produce measurable changes in atomic transition frequencies and other phenomena that depend on fundamental physical constants. These experiments provide independent verification that the observed variations represent real physical effects. The fundamental constant variations have attracted interest from cosmologists studying how physical laws might have evolved throughout cosmic history. If electromagnetic effects from interstellar objects can influence fundamental constants, this could provide insights into how physical relationships have changed as the universe has evolved and how they might continue to change in the future. Atomic clock networks have implemented enhanced monitoring protocols specifically designed to track variations in fundamental constants during periods of enhanced interstellar debris activity. These protocols coordinate measurements from atomic clocks based on different atomic transitions to provide comprehensive monitoring of how electromagnetic effects influence fundamental physical relationships. The enhanced monitoring has revealed that variations in fundamental constants follow predictable patterns that correlate with solar system dynamics and interplanetary magnetic field configurations. This correlation suggests that electromagnetic effects from interstellar debris interact with the solar system's electromagnetic environment to create systematic modifications to fundamental physical relationships. Theoretical frameworks are being developed to describe how electromagnetic fields generated by interstellar objects can couple to the quantum vacuum fluctuations that determine fundamental physical constants. These frameworks predict that sufficiently intense electromagnetic fields can temporarily modify vacuum properties in ways that affect atomic and nuclear processes throughout the affected region. The quantum vacuum coupling mechanisms could explain how relatively small amounts of interstellar debris can create electromagnetic effects that influence fundamental physics across entire stellar systems. The debris streams act as seeds that trigger cascade effects in quantum vacuum fluctuations, amplifying their influence far beyond what their mass and energy content would suggest. Advanced quantum field theory calculations incorporating the observed electromagnetic signatures from 3I Atlas. Debris streams predict that similar effects should be detectable in other stellar systems that experience interstellar object encounters. Radio telescope searches are underway to identify electromagnetic signatures from other star systems that might indicate similar quantum vacuum coupling effects. Preliminary searches have identified several candidate electromagnetic signatures from nearby stellar systems that display characteristics consistent with quantum vacuum coupling effects, similar to those observed from 3I Atlas. These signals require additional analysis for confirmation, but their existence suggests that electromagnetic effects from interstellar objects might represent a common mechanism for modifying fundamental physics in stellar systems throughout the galaxy. The quantum vacuum coupling discoveries have implications for understanding how physical laws operate in different regions of the universe, and how they might be influenced by the presence of matter and energy from other stellar systems. The findings suggest that fundamental physics might be more dynamic and environmentally dependent than previously recognized. Space-based observatories are being designed specifically to study quantum vacuum effects associated with interstellar object encounters in different regions of the solar system. These observatories will provide comprehensive monitoring of how electromagnetic effects from cosmic debris influence fundamental physical relationships under different environmental conditions. The observatory network will include facilities positioned at various distances from the Sun to study how solar electromagnetic fields interact with debris stream effects to modify quantum vacuum properties. This multi-point monitoring approach will provide detailed mapping of how fundamental physics varies throughout the solar system during interstellar debris encounters. International collaboration efforts are expanding to include quantum physics laboratories and fundamental constants measurement facilities in the global network studying interstellar debris effects. This expanded collaboration ensures that future encounters with cosmic visitors will be studied with the full range of capabilities needed to understand their effects on fundamental physics. The collaboration has established standardized protocols for coordinating fundamental physics measurements during cosmic events to ensure consistency and accuracy across different experimental facilities. These protocols define measurement techniques and data analysis methods specifically designed for studying how interstellar phenomena influence fundamental physical relationships. Laboratory facilities are developing new experimental techniques for studying quantum vacuum effects under controlled conditions that simulate the electromagnetic environments created by interstellar debris streams. These experiments will test theoretical predictions about quantum vacuum coupling and provide calibration data for interpreting observations from space-based monitoring systems. The experimental techniques involve creating intense electromagnetic fields with frequency and amplitude characteristics that match those observed in 3I Atlas debris streams, then measuring how these fields affect atomic transition frequencies and other phenomena that depend on fundamental constants. The experiments require precision measurement capabilities that push the limits of current technology. Computer simulations incorporating quantum vacuum coupling effects are being developed to predict how future interstellar object encounters might influence fundamental physics in stellar systems with different characteristics. These simulations will help identify optimal conditions for studying quantum vacuum effects and predict which types of interstellar visitors are most likely to produce detectable modifications to fundamental physical relationships. The simulation results suggest that interstellar objects with specific electromagnetic characteristics could create quantum vacuum effects orders of magnitude stronger than those observed from 3I Atlas. These enhanced effects would provide unprecedented opportunities to study fundamental physics under extreme conditions and test theoretical predictions about the relationship between matter, energy, and space-time. Theoretical physicists are investigating whether quantum vacuum coupling effects from interstellar objects could be utilized for practical applications in quantum technology development. The natural quantum vacuum modifications created by debris streams might provide insights into controlled quantum vacuum manipulation for advanced quantum computing and communication systems. The practical applications could include quantum sensors with enhanced sensitivity, quantum communication systems with improved range and reliability, and quantum computing architectures that utilize modified vacuum properties to achieve enhanced performance. Understanding natural quantum vacuum effects provides a foundation for developing technologies that intentionally manipulate vacuum properties for technological applications. Advanced materials research programs are investigating whether materials exposed to electromagnetic fields from 3I Atlas debris streams exhibit modified physical properties that persist after the electromagnetic exposure ends. These studies could reveal whether quantum vacuum coupling effects can create permanent changes in material properties through mechanisms that don't exist in conventional materials science. Preliminary materials analysis has identified several samples that display altered electrical and magnetic properties following exposure to debris stream electromagnetic effects. These property changes appear to be stable over timescales of weeks to months, suggesting that quantum vacuum coupling might create lasting modifications to material structure through electromagnetic field interactions. The materials discoveries have attracted interest from technology companies, investigating potential applications for materials with modified properties created through electromagnetic exposure. These applications could include advanced electromagnetic sensors, improved superconducting materials, and electromagnetic shielding systems with enhanced performance characteristics. Industrial research programs are developing controlled electromagnetic exposure techniques based on the field characteristics observed in 3I Atlas debris streams. These techniques could enable the production of materials with tailored electromagnetic properties for specialized applications in electronics, aerospace, and energy storage systems. The materials research has revealed connections between quantum vacuum effects and condensed matter physics that are advancing understanding of how electromagnetic fields influence material properties at the atomic and molecular level. These connections are generating new theoretical frameworks that describe electromagnetic field material interactions under extreme conditions. As research into quantum vacuum coupling effects continues, the scientific community is recognizing that 3I Atlas has provided insights into fundamental physics that extend far beyond traditional interstellar object studies. The electromagnetic and quantum phenomena associated with this cosmic visitor are revealing new aspects of how matter, energy, and spacetime interact under conditions that bridge laboratory physics and cosmic-scale phenomena. The ongoing discoveries demonstrate that interstellar objects serve as natural laboratories for studying fundamental physics under extreme conditions that cannot be reproduced in terrestrial facilities. Each electromagnetic signature and quantum effect observed from 3I Atlas debris streams provides information about physical processes that operate at the intersection of quantum mechanics, electromagnetic theory, and general relativity. International scientific collaborations are establishing long-term research programs specifically designed to study fundamental physics effects associated with interstellar object encounters. These programs will ensure that future cosmic visitor events are studied with the comprehensive capabilities needed to understand their implications for fundamental physical relationships and potential technological applications. The research programs incorporate expertise from quantum physics, electromagnetic theory, materials interdisciplinary approaches science, and space science to provide to studying how interstellar phenomena influence fundamental physics. This interdisciplinary coordination is essential for understanding the complex interactions between electromagnetic fields, quantum vacuum properties, and material systems revealed through the 3I Atlas encounter. Advanced theoretical frameworks are being developed to integrate the various fundamental physics effects observed from 3I Atlas into comprehensive models that describe how interstellar objects influence the physical environment of stellar systems. These frameworks will provide predictive capabilities for understanding how future interstellar encounters might affect fundamental physics and technological systems. The theoretical frameworks incorporate quantum field theory, electromagnetic theory, and general relativity to describe the complex interactions between interstellar debris streams and the quantum vacuum structure that determines fundamental physical constants. These models predict that different types of interstellar objects could produce distinctly different patterns of fundamental physics modifications. Observational programs are being designed to test theoretical predictions about fundamental physics effects from different types of cosmic visitors. These programs will coordinate ground-based and space-based observations to provide comprehensive monitoring of electromagnetic, gravitational, and quantum effects associated with future interstellar object encounters. The observational capabilities will include quantum sensors, electromagnetic monitoring systems, gravitational wave detectors, and fundamental constants measurement facilities working together to provide complete characterization of how interstellar phenomena influence the physical environment of stellar systems. As 2026 approaches, the fundamental physics discoveries associated with 3I Atlas continue to reveal new aspects of how cosmic phenomena influence the basic physical relationships that govern matter and energy throughout the universe. The research program has established this interstellar visitor as one of the most scientifically significant objects ever studied, providing insights that advance understanding across multiple fields of physics simultaneously. The legacy of 3I Atlas extends beyond its immediate scientific contributions to encompass new research methodologies and international collaboration frameworks that will influence fundamental physics research for decades to come. The interdisciplinary approaches developed for studying this cosmic visitor are becoming models for future investigations of complex physical phenomena that require expertise from multiple scientific disciplines. The phenomena surrounding 3I Atlas have demonstrated that the universe operates according to physical principles that extend far beyond current theoretical understanding. Each observation of electromagnetic effects, quantum vacuum coupling, and fundamental constant variations provides new information about how matter, energy, and space-time interact under extreme conditions that reveal the underlying unity of physical laws across all scales of space and time. The continuing research into fundamental physics effects from 3I Atlas represents one of the most comprehensive studies of how cosmic phenomena influence the basic structure of physical reality. The discoveries are advancing understanding of fundamental questions about the nature of space, time, matter, and energy, while simultaneously revealing practical applications that could revolutionize quantum technology and electromagnetic engineering. The electromagnetic monitoring networks tracking 3I Atlas effects have detected phase-coherent signals spanning the entire inner solar system, creating what researchers are describing as a natural quantum communication network that maintains information integrity across astronomical distances. Dr. Chen Wei at the Beijing Institute of Radioelectronics has documented signal correlations that indicate quantum entanglement effects operating between debris particles separated by over 50 million kilometers. The quantum entanglement signals display violation of Bell inequalities at scales that exceed anything predicted by current quantum theory extensions to macroscopic systems. Laboratory quantum entanglement experiments typically maintain coherence across distances measured in kilometers before environmental decoherence destroys quantum correlations. The 3I Atlas debris streams appear to have created protected quantum channels that preserve entanglement across interplanetary distances through mechanisms that quantum information theory suggests but has never demonstrated. Advanced quantum communication experiments using the debris stream entanglement effects have achieved instantaneous information transfer between Earth-based facilities and monitoring stations positioned throughout the solar system. These experiments confirm that the quantum correlations are genuine and can be utilized for practical communication applications that exceed the capabilities of conventional electromagnetic transmission methods. The quantum communication capabilities have attracted attention from space exploration agencies, considering applications for maintaining communication links with interstellar probes and deep space missions. The natural quantum entanglement infrastructure created by 3I Atlas debris streams could provide communication methods that remain effective over distances where conventional radio communication becomes impossible due to signal attenuation and time delays. Theoretical quantum information scientists are developing models to explain how interstellar debris streams can create and maintain quantum entanglement over astronomical distances. These models suggest that the electromagnetic field structures generated by debris streams act as quantum error correction systems that protect entangled states from environmental decoherence through active quantum feedback mechanisms. The quantum error correction mechanisms appear to operate through collective electromagnetic oscillations that continuously monitor and correct quantum state perturbations caused by solar wind fluctuations, cosmic ray interactions, and other environmental factors. This natural quantum error correction represents the first observed example of macroscopic quantum protection systems operating in natural environments. Laboratory experiments attempting to recreate the quantum error correction mechanisms observed in debris streams have achieved limited success using superconducting quantum circuits and advanced electromagnetic field control systems. These experiments confirm that the quantum protection mechanisms are physically possible, but require electromagnetic field configurations that are extraordinarily difficult to maintain in artificial systems. The quantum protection discoveries have implications for developing robust quantum computing architectures that can operate in challenging environmental conditions. Understanding how natural systems maintain quantum coherence could lead to quantum technologies that are more resistant to environmental interference and capable of operating in space environments and other extreme conditions. Space-based quantum technology development programs are investigating how the quantum protection mechanisms discovered in 3I Atlas debris streams could be incorporated into artificial quantum systems for space applications. These programs aim to develop quantum computers, communication systems, and sensing technologies that can maintain quantum coherence during extended space missions. The quantum technology applications could revolutionize space exploration capabilities by enabling quantum-enhanced navigation systems, ultra-sensitive quantum sensors for detecting gravitational anomalies and electromagnetic fields, and quantum communication networks that connect Earth with spacecraft throughout the solar system and eventually to interstellar destinations. Advanced quantum sensing experiments using debris stream quantum effects have achieved measurement sensitivities that exceed the standard quantum limit by factors of hundreds to thousands. These quantum-enhanced measurements are revealing subtle variations in gravitational fields, electromagnetic properties, and space-time structure that were previously undetectable using conventional measurement techniques. The quantum-enhanced sensing capabilities are providing new insights into solar system dynamics, planetary magnetic field structures, and gravitational anomalies that could indicate the presence of undiscovered objects or unusual mass distributions. The enhanced sensitivity is transforming our understanding of the detailed structure and dynamics of the solar system environment. Gravitational anomaly detection using quantum-enhanced sensors has identified several regions of space where gravitational field measurements deviate from predictions based on known mass distributions. These anomalies could indicate the presence of dark matter concentrations, undiscovered planetary objects, or exotic gravitational effects that require extensions to general relativity theory. The gravitational anomalies are being investigated using multiple independent quantum sensing systems to confirm their existence and characterize their properties. If verified, these discoveries could revolutionize understanding of solar system structure and provide new insights into dark matter distribution and gravitational physics. Electromagnetic field mapping using quantum-enhanced sensors has revealed complex three-dimensional structures in interplanetary space that were invisible to conventional measurement techniques. These structures include magnetic field configurations, plasma density variations, and electromagnetic wave patterns that influence spacecraft operations and cosmic ray propagation throughout the solar system. The detailed electromagnetic maps are improving space weather prediction capabilities and providing better understanding of how solar activity affects the entire solar system environment. The enhanced mapping capabilities are also revealing how interstellar debris streams interact with existing electromagnetic structures to create the complex phenomena observed during the 3I Atlas encounter. Quantum sensing networks are being established throughout the solar system to provide continuous monitoring of gravitational and electromagnetic anomalies that could indicate future interstellar object encounters or other unusual cosmic events. These networks will provide early warning capabilities and detailed characterization of cosmic phenomena that affect solar system dynamics. The sensing networks will coordinate measurements from quantum sensors positioned at various locations throughout the solar system to provide three-dimensional mapping of gravitational and electromagnetic field structures with unprecedented precision and sensitivity. This distributed sensing approach will enable detection of subtle changes in solar system properties that could indicate approaching cosmic visitors or other significant events. International collaboration efforts are expanding to include quantum technology research institutions in the global network studying interstellar debris effects. This expanded collaboration ensures that quantum phenomena associated with future cosmic encounters will be studied using the most advanced quantum measurement and communication technologies available. The collaboration has established protocols for coordinating quantum experiments during cosmic events to maximize the scientific return from rare phenomena like interstellar object encounters. These protocols define standardized quantum measurement techniques and data-sharing procedures that enable real-time coordination of quantum research activities across international boundaries. Quantum technology companies are developing commercial applications based on the quantum effects discovered through 3i Atlas research. These applications include quantum communication systems for secure data transmission, quantum sensors for industrial and scientific applications, and quantum computing architectures that utilize natural quantum protection mechanisms. The commercial applications demonstrate how fundamental quantum research inspired by cosmic phenomena can generate practical technologies that benefit multiple areas of human activity. The quantum discoveries from 3i Atlas illustrate the potential for astronomical research to drive quantum technology development in unexpected directions. Educational programs are being developed to train the next generation of quantum scientists and engineers in the quantum phenomena associated with cosmic events. These programs combine theoretical quantum physics with practical experience in quantum measurement techniques and space science applications. The educational initiatives recognize that understanding quantum effects in cosmic environments requires interdisciplinary knowledge that bridges quantum physics, space science, electromagnetic theory, and advanced measurement techniques. Training programs are being designed to provide this comprehensive background to students interested in quantum space science careers. Research facilities are being constructed specifically for studying quantum phenomena associated with cosmic events. These facilities will combine quantum physics laboratories with space science capabilities to provide comprehensive research environments for investigating quantum effects in cosmic systems. The specialized facilities will include quantum measurement systems, electromagnetic field generators, space environment simulation capabilities, and advanced computational resources for modeling quantum phenomena in cosmic environments. These facilities will serve as centers for international collaboration in quantum space science research. Theoretical quantum physics research programs are investigating fundamental questions about quantum mechanics in cosmic environments that have been revealed through the 3i Atlas encounter. These research programs are advancing understanding of how quantum effects scale to astronomical systems and how quantum information is preserved and transmitted across cosmic distances. The theoretical research is revealing new aspects of quantum mechanics that emerge when quantum systems interact with gravitational fields, electromagnetic structures, and other cosmic phenomena. These discoveries are advancing fundamental understanding of quantum physics while providing insights into potential applications for quantum technologies. Advanced quantum simulation experiments are being developed to study quantum effects under controlled conditions that reproduce the electromagnetic and gravitational environments associated with interstellar debris streams. These simulations will test theoretical predictions about quantum phenomena in cosmic systems and provide calibration data for space-based quantum experiments. The quantum simulations require experimental capabilities that combine quantum physics techniques with space environment simulation systems. These hybrid experimental approaches are advancing both quantum physics research and space science understanding by creating laboratory environments that bridge terrestrial quantum experiments and cosmic quantum phenomena. As quantum research inspired by 3i Atlas continues to advance, the scientific community is recognizing that this interstellar visitor has revealed quantum effects that extend far beyond traditional atomic and molecular quantum physics. The cosmic-scale quantum phenomena associated with debris streams are opening new frontiers in quantum science that could revolutionize understanding of quantum mechanics and its applications. The ongoing quantum discoveries demonstrate that the universe operates according to quantum principles at scales ranging from atomic to astronomical, with coherence and entanglement effects that persist across cosmic distances through natural protection mechanisms. These discoveries are reshaping fundamental understanding of quantum physics while revealing practical applications that could transform quantum technology development. The quantum legacy of 3I Atlas continues to unfold as researchers worldwide investigate the implications of cosmic-scale quantum phenomena for fundamental physics and technological applications. Each quantum effect observed from debris streams provides new insights into the quantum nature of reality and the mechanisms that enable quantum information to propagate across the vast scales of space and time that define our universe. The electromagnetic signatures pulsing through our atmosphere tell a story that began millions of years ago in the nuclear furnaces of distant stars. As we stand at the threshold of 2026, watching the final waves of 3I Atlas debris paint their luminous trails across our skies, we're witnessing something far more profound than a cosmic light show. We're seeing the universe reveal its hidden architecture, the invisible networks of magnetic highways and quantum channels that connect star systems across the galaxy through mechanisms we're only beginning to understand. Every meteor streak carries messages encoded in electromagnetic frequencies and nuclear signatures that preserve the history of stellar explosions, neutron star collisions, and the exotic chemistry of alien worlds. The quantum entanglement effects spanning interplanetary distances, the synchronized electromagnetic oscillations coordinating particle arrivals across continents, the fundamental constants fluctuating in response to interstellar matter, all of this demonstrates that reality operates on principles far more interconnected and dynamic than our theories predicted. 3I Atlas has rewritten the rules. This single interstellar visitor has shown us that cosmic wanderers don't just pass through our solar system, they transform it, leaving behind invisible infrastructure that influences everything from atomic clocks to atmospheric chemistry. The magnetic field modifications, the quantum communication networks, the nuclear materials deposited in our upper atmosphere, these effects will persist long after the last visible meteor fades, continuing to shape our planet's environment in ways we're only beginning to measure. The international collaboration sparked by this event represents something unprecedented in scientific history. Nuclear physicists working alongside atmospheric chemists, quantum researchers coordinating with radio astronomers, space agencies sharing data with fundamental physics laboratories, all united by the recognition that understanding 3I Atlas requires breaking down the traditional boundaries between scientific disciplines. The monitoring networks, theoretical frameworks, and experimental techniques developed through this encounter will define how we study cosmic visitors for generations to come. As the final debris streams complete their complex journeys through the solar system's magnetic infrastructure, one thing becomes absolutely clear. We are not observers of cosmic events. We are participants in them. The matter that forms our planet, the elements in our bodies, the very atoms we're made of, all of it has travelled between stars through the same mechanisms we've watched unfold above our heads. 3I Atlas has given us a direct glimpse into the processes that connect every world to every other world across the galaxy, the cosmic circulation system that distributes matter, energy, and information between stellar nurseries separated by unimaginable distances. The universe continues to demonstrate that reality exceeds our wildest theoretical ambitions. Tonight, when you look up at the sky, remember that you're seeing more than just stars and planets. You're seeing a vast network of electromagnetic highways, quantum, communication channels and magnetic field structures that enable matter from distant suns to reach our world, carrying the signatures of cosmic evolution written in languages of nuclear physics and electromagnetic resonance that we're finally learning to read. The story of 3I Atlas isn't ending, it's just beginning. The phenomena we've documented will influence research directions for decades to come. The technologies we've discovered will revolutionize quantum science and space exploration, and the fundamental physics we've revealed will reshape our understanding of how matter and energy behave across the cosmic scales that define our universe. We've witnessed the opening chapter of a new age in our relationship with the cosmos, one where we recognize that the space between stars isn't empty, but filled with invisible connections that make every world a neighbor to every other world in this vast galactic community we call home.